Hello, welcome to another stream. How about that? How about that? Bet you didn't expect that shit to happen. Hello, hello, 7001, Agduk Out 9, Sasalala, Guan the Third, Police Cone, Fink, Yatanasov, hello, really glad to see you all today. Jir, I hope I pronounced your nickname correctly. Johnny Richard, hello. Ivan Ho, hello, welcome. So today is Wednesday, if I'm not mistaken, and that means today, according to the schedule, we are doing development. That's what we're doing today, we're doing development. Yeah. Oh my god, I could do.
Thank you for your streams, Mr. Streamer.
And thank you for your subscription, Mr. Viewer. Thank you so much for 18 months of Tier 1 subscription. Thank you. And welcome to our epic viewer club. That's right, we're all our viewers here. So, yeah, thank you so much. This is a really long support. Thank you. So, today we continue developing our virtual machine in C. So, it's called BM, right? It's a project where it's like a half of a research project, half of a recreational project. So in this project, I'm trying to create a very simple virtual machine for languages. Like it's kind of similar to LLVM, I suppose. You can think about it this way. So it has its own like machine, its own architecture. It has its own set of instructions. It has its own bytecode, right? And it has its own set of tools that allow you to develop for that virtual machine. And on top of that, we're developing translators that take the bytecode of that virtual machine and translate it to x86-64 native code. And in the future, we're going to have more different translators. Java virtual machine, yes, exactly. That's what we're going to do eventually. So we have issued for actually translating BASM to WASM, to WebAssembly, and I didn't see any problems with, for example, developing something that takes a virtual machine bytecode and translate it to JVM. Why not? JVM could be, so it could be something like BASM to class or to JVM, I don't know what it's called, but yeah. BASM to WASM, yeah, we do have an issue for that. Like, I mean, it's if you go to the source code of the project and go to the issue tracker, not really source code, but the repo, you will find an issue that is literally called like that, BASM to WASM. I'm not even joking. Here it is. It was created 2 days ago. So BASM to WASM. So yeah, eventually we can try to do that. I didn't see any problems with that, but we need to develop the tool set a little bit more, so it's a little bit easier to do this kind of development. C to BASM, maybe we can also try to do BASM to C. Why not? As far as I know, for quite some time, JAI used C as an intermediate language. It was, I'm not sure if it still uses for some cases, but like at the very beginning. So JAI was basically translated to C, and then that C was compiled and stuff like that. Have fun reading JVM specifications. Thank you, Nate. We'll see. Maybe I'm gonna just create an issue for JVM translation and never do it myself. You know, I'm gonna acknowledge that. Yes, we kind of want to do that, but just somebody else do that, not me. I don't know, we'll see. So maybe for some simple things we can do that, do some simple translation. I mean, if you think about it, x86-64 is also a pretty complex beast, but yet we still have some sort of a translation to it, right? So we don't have to support like everything. We can just support like a small subset that makes things work, and then eventually build up on it. So yeah, hello Benny Darshan, just Sophie, hello everyone who just joined. Are you dealing with the register allocation x86? No, I don't. Or are you treating it like a stack-based machine as much as possible? Yes, I'm treating it as stack-based machine as much as possible. So I have a couple of ideas on a stack allocation actually. On register allocation, right? So for example, we can like mentally treat like first n elements on the stack as elements on the registers, right, and have some sort of like a smart subsystem that actually, you know, resolves all of that. And maybe that's basically what's called register locator. I don't know, we'll see. But all of that is just, you know, theoretical. We have some other things to do. Oracle doesn't employ programmers though, only lawyers. It's kind of ironic that I know some people who work at Oracle as developers. So I guess if it's a joke, I do understand the joke. Yes. To be fair, you can think of Oracle as Disney of software development, right? And the thing about Disney, unironically, no joke, Disney has more lawyers than animators. Seriously, it's not a joke. Like, they have significantly more lawyers than animators. So yeah, nice. Let me see. Let's fetch some stuff. I did a little bit of work off screen. I did a little bit of grind off screen. Hello, Postcom-Sci. Hello, Daniel69. Welcome, welcome. And one of the things I did, I updated editor support for Emacs and Vim, so it supports more keywords. So they know the new keywords are now supported by both Bosom, Emacs and Vim. And another thing I did, I actually did. I got rid of the bind directive. You guys remember how in the Bosom we had a bind directive, right? Where you could do a bind. So you can do something like M69 and you can bind a value 69 to that thing. So you're welcome, actually. Yeah. By the way, yesterday I actually gifted like 35 subs to Tsoding channel, so they were picked randomly. And the reason why I did that is because I drew a new emote. Yeah, I didn't have a slot for that emote, and I couldn't think of what emote to remove. And it was like, you know, 30 something subs away from the next slot. So I decided to invest into my channel and just gift a bunch of subs so we can have additional emote without removing anything. So, and everyone who got the sub, congratulations. So yeah, you now have a sub. And also you can use this emote. 35 gifted, yes. So anyway, so I got rid of bind, so there's no bind anymore, and if you can try to use it, there will be interesting error message. Yeah. So bind directive has been removed. Use const directive to define consts and native directive to define native functions. You see? So if you want to define a constant, like just a regular constant, you have to just do const, right? But if you want to define a number for a native function, you will have to use a native directive. And semantically, there's not that much difference between them. Yeah. So you're really close, Aguduk. Semantically, there's not that much difference between them. The reason why I introduced all of that is because I actually shoot myself into the leg quite often by doing something like call write, where write is a native function. So now with this separation between kinds of bindings, we actually have three kinds of bindings. The first kind of binding is constant. The second kind of binding is a label. Yes, we do have a separation for labels. And the third kind of binding is native. So this separation allows us to do the following errors. Let me show you. Trying to call not a label. Write is native, but the call instruction accepts only literals and labels. So now we have a little bit more type safety, so you won't be able to do something like that, so I won't be able to shoot myself into the leg. What's interesting is that you can also assign labels to an entry. So if you have a constant, if you put m here, it will also throw an error saying that something like trying to set a const as an entry point has to be a label. Right, so something like this, but they still share the same namespace. They still share the same namespace. Oh, into the food. Thank you so much. Yeah. All right. Are you guys like seriously counting how much I paid and how much I got back? Just enjoy the subs. God damn it! Oh my god. All right. So this is basically the changes that I made. And I think they're going to be useful in the future. I think they're going to be very useful in the future. We'll see. We'll see. The winner gets a tea, that's for sure. By the way, speaking of tea, today we're drinking a regular ass tea from the same brand, but it's just a regular one. It's not an Earl Grey or anything. So I still don't understand what the fuck is that brand, but apparently it's I think it's a Russian brand. So yeah, so let's actually do unboxing. Yet another unboxing content that you were waiting for. So bags or loose? It's actually loose. There we go. So there is like a tin foil bag inside of it. A little bit of a TSMR. All right. So let's do the opening. It's a K-Commerce brand. Yeah, I figured. So we actually have shit ton of our local owned brands that try to mimic something from Europe. It's quite common in Russia. Where's the referral link? It's not sponsored by. This is not sponsored, by the way. This is whatever I bought in a store across the road. I mean, if the store wants to sponsor me, yeah, maybe. But it's not an ad. Okay, so can I open that first try without actually screwing up the packaging? Let's find out. First try? I think I first try the opening. Yeah, boy. Yeah, boy. There we go. Nice. Sponsored. Yeah, I'm sponsored by KGB. Since it's a K-Commerce brand, obviously I'm sponsored by KGB. Right. So I'm not gonna do, not gonna make any tea right now. Just a little bit later. I just want you to pre-open it, right? So I don't have to open it later. So, you know, and then I have another paper clip. I have shit ton of them, by the way. So I'm just using them to seal the packaging of all sorts of things. Yeah, it's loose. It's loose. It is loose leaf tea. Alright. So yeah. So what's that shit? What's that shit? Okay, let's remove all of that. Cool. Referral Zozin, yes, referral Zozin. Okay, let's take a look at what we need to do today. Oh, by the way, I also updated so it highlights. Just a second. I also updated the mode so it highlights the character literals, right? Also string literals and stuff like that. So if you can push the character literal like this, and it's a valid thing, and it's going to be translated as the ASCII code of that character literal. So yesu kawai desu. Oh, another thing, if you try to call a native, right? If you try to call a native, oh well, I mean, I already demonstrated that. If you can try to like use native on something that is a label, I think it will also fail. Yeah, trying to invoke native function from a binding that is label. Binding for native functions have to be defined via native boson directive, right? So that's basically what it is. It's pretty cool. It's pretty cool, not gonna lie. So we have a type safety in assembly. Can your NASM do that? Can your NASM do that? So let's do something simple. Entry point already set error does not tell where exactly the entry has been already set. Okay, so let's take a look. Essentially, yeah, if you try to set the entry 2 times, our compiler does not allow you to be a 2-time champion of the boson, unfortunately. Maybe fortunately, depends on how you look at it. So essentially, if you define something like second main, right? So here is the second main, and try to do something like this: entry second main, right? If you try to compile this thing, it will say entry point has been already set. It tells you like where it's you're trying to redefine it, but it doesn't tell you where it was originally set. And I think it could be quite important, especially if it's in a different file, because it could be sometimes difficult to find it. So I think this is something that we have to keep track, and I don't think it's that difficult to do. This is Vim actually. Right, so if you take a look, it's a Vim. So the title of this editor is Vim. So yeah. So let me see. So I think I'm gonna go and do it like that. So let me create a separate branch. 1, 2, 4. 1, 2, 4. Dude, that's so can't do. You forgot to also ask for mesh shaders, I think. All right. So I recently introduced a type called file location. So file location basically keeps track of the file path and line number. And also file location has its own formatting printf macros. So if you have a file location, you can easily print it on using printf or snprintf or something like that. So in the bosom, we keep track of the entry, deferred name and deferred location, right? Deferred name and deferred location, but deferred location is where the entry is defined. We need another file location. We need another file location for the original entry, if you know what I mean. For the original entry. But maybe we can always set. Yeah, I think we don't need to separate between deferred entry location and entry location. Just always do entry location. I think it's a good idea. So, all right. What about your shaders? What? I use mesh shaders every day, 3 times a day. Is that what you wanted to know? All right, so we have an entry location, and where do I set the entry? Let me find. All right, so this is where I set the entry, right? This is where we set the deferred location, and this is where I do this thing. Entry location is the current location of the translation. There we go. So now we keep track of it. And if bosom has an entry, right, instead of doing FLFMT location, right, we also have to say where exactly it's defined. Let me see. So entry location has been already set. So it's going to be FLFMT, the original, the first entry. How to say that? Definition? The first entry point, like that, and it could be actually a new line. And it's going to be FL_arg, and it's going to be bosom entry location. Bosom entry location. There we go. There we go. There we go. And now, if we try to recompile this entire stuff, right? Let me see. Let me see. So this is a bosom, and I set another entry somewhere here. Entry. Well, let's put 69 here. I think you can set numbers in an entry, and it will tell you this thing. Okay, entry point has been already set. The first entry point. So yeah, you can always jump back to where it was already set. But the interesting thing here is, can I slightly change this stuff? The first, where's BM? Can I say something like note, the first entry point? Yeah, a note or something. Like a second. Yeah, there we go, the first entry point. So the reason why I want to have it like that is because what if I accidentally put an entry point somewhere like in here, like dump u64, and right, you look at the original thing and you don't know what the fuck is going on. So in the original message it looks like this, right? So here's the entry main, but it's already set. So, and this is where it was set. It was set in a different file, and the error message actually tells you, okay, dude, it was set in a different file. So yeah, and then you can, oh, okay, so it's a standard library, I don't have to have an entry point here, and now it compiles. So yep, that's pretty cool. So we keep track of where the entry point was already set, and if you try to reset it, it will also tell you where you set it in the first place. So that's actually very useful, I think. I already like Bosom better than Nasm because I think it just like provides you like very good type safety things. Yeah. All right, let me commit that. 1, 2, 4. Keep track of the original keep track of the entry location. But I also use the thing called deferred entry locations, which I'm not sure is a good idea. So I think we need to get rid of the deferred entry location. So the difference between like entry location and deferred entry location, so this is just an entry, right? It's just an entry. The one that uses labels is a deferred one. The reason why it's deferred one is because it uses a label, and labels are not known until we finish the first pass of the translation. So it's actually a two-pass translation. So on the first pass, we gather all of the labels and stuff like that. And on the second pass, everything that refers to these labels gets resolved, right? And that's why, for example, you can have an entry, but you can define a label after you define an entry, right? So basically to enable this kind of stuff. So it's a two-pass translation. So, and this is what it means to, like, for an entry to be deferred. Like, you refer to this label, but we don't know that label yet because we haven't finished the translation of the whole thing, right? So that's basically what it means. Yeah, and I keep track of the deferred entry location for error messages related to the deferred entry location, but I think it's kind of redundant. I think we should get rid of that. Deferred entry location. So here's entry location. So we have entry. We also probably have it like an indicator that we already set the entry, and also deferred entry binding name. All right. So let me try to compile that. And what we're doing here, we're setting the location. It does not matter anymore because we always set the location regardless of whether it's deferred or not. And in another place, we're referring to deferred entry location. We can just use entry location. And in here, we can also just use entry location. And I think that is it. So now we can test some things, right? For example, I can do something like dump u64, right? So this is what we're gonna have here. It will tell me, yeah, so here is that. Here's the error, and this is the entry point. Cool. But if you try to refer to a label that doesn't exist, I think it should also, I think it will fail a little bit earlier. So if I try to do something like this, yep, unknown binding, there we go. So it still reports in the correct place. Cool. So by the way, unknown binding error was generated on the second pass. Because on the first pass, we don't check whether we have bindings or not because we haven't collected all of the bindings. So that error generates on the second pass once we know everything and we're trying to resolve all of the deferred references, and only then it gets generated. So yeah, two-pass compilation. It's pretty cool. Cool. Yesu, kawaii desu. So now let me actually compile everything with x86-64. I already compiled everything with x86-64. Nice. Okay, but what about 3-pass? Why do you need 3-pass compilation? Why do you need 3-pass compilation? I'm actually planning to add meta compilation, where let me show you what I mean. So you have the following feature where you can do const hello and then hello world, right? And what it does, it actually adds this string to the internal memory of Boson, to the static memory of the virtual machine, right? So I want to have a feature, something like this, meta hello and end. So essentially what this thing will do, you put your code in here, literally. So you do something like push 1, push 10, write 8, and so on and so forth, and you write something to the memory. So what this thing does, during the translation, it will take this thing, evaluate during the translation, because we have a virtual machine, so it can meta-evaluate it, and then the memory, so the resulting memory of this evaluation is going to be baked into the memory of this program. So basically at compile time, using Boson itself, you can pre-compute the memory. For example, you will be able to pre-compute Fibonacci numbers, right? And they will be baked into the memory. And then the beginning of that memory is going to be at hello, so you will be able to do something like push hello and then read 64 to read a number from that memory that you computed at compile time. But I haven't implemented that yet. So yeah. Yeah, it's CTF-E is compile time F evaluation. I don't know what F stands in that CTF-E thingy. Not sure, but this is my idea. So yeah, but I haven't implemented that yet. I think it's going to be interesting to implement. Function, yeah, it's more of like a function evaluation, but it's like a meta program. You put a program inside of a program, and maybe you will be able to actually have them nested. Because why not? You can probably nest this meta evaluation as much as possible, but I'm not sure how useful that would be. I don't know. Run hello, yes, exactly. Run hello. But in my case, it's gonna be like this, right? Run hello. So I'm thinking about something like that. So you can have small programs in Boson. Oh yeah, Jai also has bake, but bake is like carrying, if I remember correctly, right? So if you have a function, I think this is how we define it, like with a couple of arguments, right? And then you can do something like bake f, like this, and that carries, that creates a new function with like this argument bound or something like that. If I remember correctly, of course. Like I know Jai only by watching John's streams, but I never actually tried it myself. The old Tsoding tradition is to argue with bots in chat. Yes, that's what we do on Tsoding channel. All right, so I'm not gonna do that. Keep track of the entry location. Remove entry deferred. Deferred entry location. There we go. And we're gonna push that right into the repo. Right into the repo. Okay, so I think we're ready to make a pull request. The first pull request of the stream. How about that? It's only 40 minutes into the stream and we already have the first pull request. Isn't that amazing? Okay, so we're gonna do keep track of the entry location. No, this is not what it is. Entry point already set, error. Okay. Report original entry point location on entry point resetting, and we're gonna close that like this. There we go. There we go, there we go. I feel like a legit language developer. That's pretty cool. It feels really nice. And now I understand why people like to develop languages. It makes you feel like you're doing something important. It makes you feel like you're doing something serious. Right. Do we care about 3 occurrences of entry? It doesn't matter because the compilation will stop at the second one. So you won't even ever see the third one. So it just stops at the second one and reports you. Here's the first. And it doesn't matter if you have 4 occurrences or 5 or 6. It doesn't matter. It stops at the second one and just refuses to translate it any further. All right. No error recovery. Why? Like the experience has shown that if you encounter an error, it's better to just break and crash and report to the user. Like trying to collect as many errors as possible results in GCC syndrome, right? So you all seen the GCC compiler errors; they're unbearable. Wait, you're writing your own language? I've been listening, but I didn't know that what you're doing. Not really. So I'm developing a virtual machine because error recovery is important for LSP. Well, we're not developing LSP yet. We're not developing LSP yet, but once we start doing LSP, maybe we can think about that. All right. So we're developing a virtual machine, right? We're developing a virtual machine, and virtual machine has its own bytecode and it has its own assembly. And since it has its own assembly, right, we're developing a translator for the assembly. So yeah, and if you take a look at the examples for the past like 40 minutes, I was showing different examples in different languages like this, and this is the language that we're developing. This is not like a real assembly. It's our own assembly that we developed from scratch. So it's not like it's something existing. No, we developed this thing from scratch, including the syntax highlighting, sure. So yeah, you won't be able to compile it with any other assembly compilers except the one that we have here. And it's not a thing. Like these instructions are not a thing. Seriously, it's made up instructions that we made up ourselves. So, yesu, kawaii desu. Alrighty, so are we ready to... we already merged everything, okay. Will you throw a warning if you misstep space in code? No. I'm not forcing any particular style on the developers. This is not the thing I want to do. For some reason, modern languages are trying to force you into a particular style, and I don't really like that. So we're not forcing that. Not forcing. Hahaha. Alright, let me actually see if we can purge some of the to-dos and whatnot. Okay, so there's no way to examine the memory in BDP. We already fixed that. Is there anything else? Entry point, yeah, we already fixed that. I guess that's it. Yeah. Oh, my repo is dirty. I need to delete some branches. Okay. Sure, go ahead. You have my blessing here, hosts and plots. Go delete some branches. All right. So let me see. So what's gonna be the next thing that we want to implement? Maybe we're gonna start developing print F64 purely in assembly. Constant falling. Nah, I don't really want to go into that. Top of this allocator. Not all of the examples are translatable with BASM. Alright, so let's actually do the real work. Let's implement print F64 purely in BASM. So for the past several streams, what we were working on? We were working on taking all of these native functions like print I64, print U64, and re-implementing them in BASM itself. Right, and there's the last one that we haven't implemented yet. So we need to implement print F64. So we need to print floating point numbers, and we need to implement that in BASM. Yes. Yes, we do have that issue. It's a classical MSVC issue. I think it's already fixed. Maybe it needs to be closed. I don't remember. Anyway, so we already implemented print F64 in assembly, purely in assembly, by using well-established old algorithm. So what we need to do right now is we need to translate that algorithm to BASM, right? We need to translate it to BASM, And that's pretty much it. That's pretty much it. So the main part of the algorithm is actually print frac. Right, the main part of the algorithm is print frac that prints the fraction. Right, so essentially the algorithm, if you write it in C, would look like this. So where's my C mode? So imagine that you have printf64, so and you accept this thing. So essentially what you do, you take the integer part, right? So x, and you convert it to int 64 in 64t, right? So this is what you do, and then you print I 64. There we go. So this is what you do. After that, you need to take the fraction of this thing. So you'll probably have to have some sort of like a function that takes a fraction of it, and then you print the fraction. So printing int64 is already a well-known algorithm that we have implemented, right? And then we only need to implement an algorithm that prints the fraction of that floating point, right? Yeah, this is the only thing that we'll probably need to implement in Boson. And that thing is already implemented in assembly here. So we'll just have to translate that little thing. Oh, all right. Are you guys ready? Are you guys ready to do that? I think, yeah. Maybe before we're gonna do that, I'm gonna make a cup of tea, but I'm not sure if I want to go into that. Okay, so re-implement purely in assembly. Yes, let's create 130. And SRC, BM, not BM, but examples, natives, cousin. Is feedbackz supposed to segfault? No. All right. If it fails, like everything like native is very unstable. It's very unstable. So if there's any problems, maybe it makes sense to submit like a pull request, but an issue or something like that. So let me see. So we need to do something like similarly to print positive, right? Similarly to print positive, as we have print positive, we need to have print frac, right? And this entire thing expects values less than 1. It expects values less than 1. No. So maybe I need to open that PDF that we were looking through, because I think I'll need to use it as a reference for my development. I have a link in the source code itself. So here is the link. So this is the thing that we use here. I'm gonna put it here. PDF like this. So this is the paper that we use to implement this algorithm, and the algorithm is somewhere here. Here it is. So here's the algorithm. If I remember correctly, yeah, we start with the F, and then we have that. We also need to pre-calculate this B, right? So yeah, minus n is basically the precision, right? N is basically the precision, so we'll have to put that precision there. So the precision could be something like a const, right? So the const print, maybe we're gonna go with frac precision, and we're gonna say that we are gonna be printing 10 characters, right? We're gonna be printing 10 characters after the period, right? 10 characters after the period. So the next thing I want to do, I want to actually be able to pre-calculate a minus b, like minus n, b to the power of minus n. So the question is how we can do that. So b, if I understand correctly, is the radix of some sort, like it has to be 10. So let's go and do that. So maybe I want to have a separate function for that. So how should I call it? Not quite sure. Power minus n. So yeah, I don't know how to call it. Sorry for topic. Any tips for learning math for CS? Why? Why do you need to learn math for CS? I don't have any tips. I'm sorry. So you can just try to learn it. I don't know any math. That's why I cannot tell you like any tips. I'm sorry. I'm not even a programmer, so that's the problem. Not even a programmer. So I think you're asking the wrong guy about this kind of stuff. Sorry. I just sit here all day, shit posting on the internet, and just drinking tea. Seriously, I'm not even employed, and you asking me about tips of something like something math, CS, something. Really? Like, why? This is like literally Russian hobo sitting streaming and shit posting on the internet, and you asking me? That's really strange. Like, why? You could have actually went like to somebody who's like really established in CS, or maybe ask like a CS professor on how to learn this guy. Like, literally, it's like me? Come on, dude. I can give you tips on shit posting on the internet, so that's for sure. But CS, I don't care. Alrighty. So I wish I could come up with the name for this function though. B. I don't know how to. Let's call it B. So that's literally the name of the function. It's going to be called B. So what it accepts? It accepts n, right? It accepts n. So what's interesting is that when you push n, on top of the stack, you're going to have a return address, right? You're going to have a return address. So the first thing you want to do, you want to swap 1 to bring n to the top of the stack. So after that, you probably want to keep track of the values, so of the return value. So you want to push this thing here. So after that, we're going to just push 10. So minus n. So, and essentially what we need to do here, we need to keep multiplying it by 0, 1. For some reason I cannot think really straight right now. Print frac. We're trying to pre-calculate this thing, right? So here's the loop. You actually start with 1, right? You start with 1 and you keep multiplying it by 10th. Yeah, so essentially you have to start with 1 and you have to multiply it by 10th and time. So that's what you need to do here. So what's funny is that maybe you want to swap it one more time. Maybe you want to swap it one more time to get something like this, to get the initial state right here. And then we can do B. B loop. And yeah, so first we want to check the condition, the original condition. Right. We want to duplicate the current value, right? So, what if we don't swap it? Because we can always duplicate it like this. Duplicate 1, right? If you duplicate 1, you have 1 at the top, right? You have 1 at the top. Then you can push 0, right? You can push 0. And after that, you want to compare these two values. And the values you compare on the top of the stack, they usually go like this, n and 0. And what you want to compare is that while you want to skip the loop if this thing is less or equal, okay, less or equal in terms of integer, less or equal to, yeah, just literally less or equal, right? And this is going to be the result of the separation. So if you do less or equal, this is the result of the separation. And so this is the loop and this is the condition. And if it's true, you want to jump, shit, where is my thingy? I couldn't be bothered, I'm really sorry. But I mean, I'm probably gonna use the new operations. So I just need to update my stuff, whatever. Value buffer, bosom, okay, there we go. B loop end, so that will jump to the end of the loop. And the B loop end is gonna be located somewhere like here. B loop end right here. So that's essentially what we do. So we dupe 1, push 0, we compare it, and if it's true, if we're less or equal than 0, that means it's time to drop the entire thing. So after that, what I want to do, I want to push 0, 1 onto the stack. So here's the 0, 1. By the way, I'm pushing 1 here, and this also has to be 1. Right. Then I'm multiplying them as a floating point. Right. And something goes like this. Also, I need to swap 1. I need to swap 1, which swaps things like that. Then push 1, right, and minus I, and that subtracts that thing here. And then we want to swap 1 once again, and we're gonna end up with this thing. Yep, we finished the whole, like, a single loop in here, and after that we unconditionally jump back to the loop, to the beginning of the loop, right? B loop, we can even call it B loop begin, and here's a B loop begin. So this is begin and this is end. So this is how we organize the loops. So this is the condition that we check. If the condition is true, we're gonna skip the whole loop. Then we perform the body of the loop and we unconditionally jump back, and this is how we organize all that. So at the end of the loop, right, at the end of the loop, we're gonna end up with return value, the final return value, and 0, right? So essentially what we need to do here, oh yeah, that one is very interesting. So you're gonna have that on the stack, right? So we need to get rid of this entire thing here. So I'm gonna swap 1. So swap 1, that gives me this thing here, which I can then drop, right? I dropped it, and then I'm gonna do swap 1 yet again to put the return address at the top of the stack, and then I return from the function, and after I return from the function, I have the final result. There we go. So I implemented B function, which computes 10 to the power of minus n. So it accepts the n. Actually, it accepts 1 to the power of minus n. Right. So this is basically what it computes. Hopefully that will work. So this is like a very important function for the print fraction algorithm, and one of the things we want to do right now, we want to test how it works, right? We want to test how it works. Now, so let's do test bosom. I'm gonna include examples natives bosom, and we're gonna have an entry point, and we're gonna define an entry point like this. Right, so what I'm gonna push here, I'm gonna push 0, and then I'm gonna call to B, and then I'm gonna print f64. So yeah, so we still have print f64, which is a native function, right? So, and yeah, let's try to see what's gonna happen if I try to compile it. Okay, no such file examples. Oh, because it's natives hasm. That's right. Wait a second, include doesn't report its own location. Let's quickly fix that. This is actually very important. Include has to report its own location. It is very, very goddamn important. It is very, very goddamn important. So let me see. It's going to be include. There we go. And okay, exceeded my maximum level. Wait a second. Could not read file. Oh shit, I see. Could not read file. Yes, okay. Arena slurp file. Ah shit, I see. So Arena slurp file actually has nothing to do with the translation process, and if it cannot slurp the file, it just crashes the whole application. So we need error recovery. Oh, here's the thing. So L9 was talking about like error recovery and stuff like that. When I code a program for the first time, right? So initially I don't care about error recovery, right? Because we don't have enough information about like how to recover and stuff like that. So essentially I basically, if I encounter an error, I just crash everything, like regardless of anything, and it lets me code really, really fast. As I add more and more features, the more error recovery is required, and only then I actually add it. And for example, here we need to add error recovery, for example, if the file doesn't exist. Yeah, because of that, I can just add additional parameters to that, or maybe do something else. So yeah, so this is my approach. Not sure if it's a good approach, but it works for BM at least. Right, so yeah. Okay, so let's actually find and put a to-do. So we slurp the file. Where do we slurp the file actually? To-do include directive does not report location if the file does not exist. Does not exist. Alright, so okay. So oh shit, trying to call not a label, printf is native. Okay, so I keep making the same mistake and it actually saved me. So yeah. Investing time into introducing different kinds of bindings was actually beneficial because it literally called it right away. Holy shit. Yes, okay, so that was useful. Ah, nice. Actually useful features that, you know, prevent you from doing something stupid. Okay, so mult f, yeah, we have something like this. Oh yeah, speaking of fib.exe segfaulting, we introduced a lot of features recently that are not... Yeah, okay, here's some plots. If you're still there, are you still there? Yes, it's supposed to segfault, everything is broken.
Sodin Pagding.
Thank you, Drakik Zorn, if I hope I pronounce your nickname correctly, for 3 months of tier 1 subscription. Thank you, and welcome to our epic bug reporting club. So you already submitted the bug. Okay, so I think to fix the bug, we need to go through all of the fix me's here and implement them. So that's what we'll need to do. So yeah, we're going through the like major transitions and stuff. So that's why this thing doesn't work. I'm really sorry about that. All right, so this is going to be multf, and it's going to be printf fix me multf, and I guess that's gonna be it. Yeah, thank you so much. Thank you. So signed word immediate. Oh shit. unsigned word. How can I have unsigned literals then? Is it possible for me to have unsigned literals? Okay, so this is a push instruction. Let me try to look at the translation. Bosom to Nazm. Push instruction. So it uses U64. Okay. Nazm unsigned literal. How do you do unsigned literal? God damn it. Maybe it's you. But I don't want to guess it. I want to... Okay. Number literals. This is such a bad... Okay. Constant. Fucking surprised how shitty it is. Literals? It doesn't have... Okay. I mean, I probably can use hex, but alright. Where do I add you, though? Like, you say you probably guessed it, but where do I add it? Do I add it here? I don't really like to guess this kind of shit. Like, it's like, why do I have to guess it? Documentation should tell me, and it should be Googleable easily. Of course not. Of course it's not here. Yeah, you just literally try to guess it. I don't know why I even tried to... Okay. So how can I do hex for these numbers? Hex. 64 as hex. Probably PRX. I'm pretty sure it's PRX. Yeah, X64. Okay. So, and then if I try to compile this thing. Okay, so it has a syntax error, right? This is expected. And now, maybe I want to actually make it big so it's looks a little bit better. Right? Yeah, so it looks like this. And I'm gonna do like 0x. Cool. There's no CMP because 64 bits, but so keyword is 64 bits, isn't it? Is keyword 64 bits? So, but it's, I mean, it's signed and signed. Oh my god, it's not that. How can you stop this warning? Oh, Teva, I accept. Please don't tell me Nazem doesn't have unsigned literals. Please don't tell me that. This is bullshit. Signed word immediate exceeds bounds. How? Keyword. Okay, Nazem keyword. Keyword 64, yes. So it's just, I don't know, man. This is really frustrating. This is really frustrating. And Google doesn't even like know. It's almost like nobody knows what the fuck I'm talking about. The fact that the documentation didn't mention nothing, maybe because it's not support for unsigned ints. Yeah, it's so fucking dumb. Holy shit, I'm so frustrated. D word. What? Like D word? I'm not even doing D word. Dude, I'm using like literally keyword. Do you want me to put keyword in here? Like the error message doesn't even make any sense. Like, no, I'm not doing D word, dude. Like I'm doing keyword. Come on. Okay, so what if I put keyword in here? I'm actually so surprised I'm wasting my time on that. Okay, you can put keyword in here, but it still says D word. Really? Is that a... Wait a second, they're talking about some sort of a bugs. Right, so there was like a bug. Well, you may add so Nazem would not optimize sources. The real bug is in the report code. The directive is called beats not use. Against the following combination. 64-bit constant. Is it really 64-bit constant? Holy shit. Ooh. This is not a D word. I ran out of ideas what to Google, like, because the obvious thing is going to be unsigned literals, but obviously the authors of Nazem call that stuff somehow differently or don't call it at all. So I'm thoroughly bamboozled, I think, confuzzled. Alright, so I'm gonna go to the kitchen and turn on the kettle, and I'm gonna be back and we'll try to resolve this problem afterwards. Pricks. I just realized it's Pricks64, and the fact that it's a valid name from the C standard is actually Pricks64. Nice one. Welcome back. Oh, you found something. You found something. Thank you. Thank you so much. Let me see. most x86 don't take 64-bit immediately, unless I'm very mistaken. You have to move through the RAX register. Okay, so that's a good point. So that means it's not a NASM bug, right? It's not a NASM bug. Okay, so let's try to do something like this. We're moving to RAX, right? And after that, we're moving the value from RAX in here. That's a very, very good point. Okay. Thank you so much. Thank you. You're VIP now. Wait a second, did I actually turn on the kettle? I don't remember. Oh yeah, I did. Thank you. Very cool. So that makes sense. So Google forward again. Yes. Alrighty. So cool. Nice. So and if we go take a look at the build examples, ASM. So I'll take a look at some of the push. Yeah, so we literally, yeah, this is a pretty good example. So we just push that. Alrighty. So what I was doing? Does anyone remember what I was doing? I forgot what kind of issue I'm solving here. So it's one of those situations like you go to the like yak shaving sessions for so deep. What the hell I was doing? I literally do not remember. So I have this. Okay, so this is the function that converts this stuff. Does not report location. Yes, okay, so this is a to-do. But did I have... Okay, so I have a test function to test... Okay, cool. Yeah, I call that, and I just want to print that thing. All right. Ooh. Yak shaving is real. Holy shit. Oh my god, I forgot to detach it from this session. Forgot to detach it from the session. Shouldn't this work without using hex? Yes, it should. So, test BM. Okay, stack underflow. Perfect. And this is because I should actually halt. Cool. So this is 1. And if I add 1 here, right, I'm gonna recompile this thing. Yeah, so essentially if I put like 10 here, but I don't have to do here 10 here. Print, I think it's frag precision. Yeah, frag precision. So I'm gonna put a frag precision, recompile it one more time, and it's gonna be, oh shit, the precision actually here is actually too long. Huh. That's very interesting. So it literally looks like 0. So let me go to bm.h, native print f64. What do we use here? Make constants that start with reserved for compiler use. There's no need for that right now. So okay, that's a lot. Let's say that maybe 6 should be all right then. Okay, so yeah, there you go. So we can compute this for any n almost. So natives, cool. So the question is. So let's go ahead and implement this entire thing. So we don't need to keep track of k, in my opinion. So here's r, which is f, right? Here's r, which is f. And f is an input, if I remember. It's a fraction, yeah, so it's supposed to be the fraction. It's supposed to be the fraction. And we also will need the floor. Yeah, we'll also need the floor function. Okay, so next thing we need to implement the floor. There we go. So I just remembered. And in the original implementation, we had a lot of different auxiliary functions. I think we should start with them. We should definitely start with them. We have fubs. So we have frac, we have floor, and I guess that's it. I think that's it. So let's implement fabs. Let's implement some fabs. So to do floor, floor is not implemented. Okay, and fabs. Okay, my tea is ready, by the way, so I'm gonna quickly go to the kitchen and pour myself some hot water, and I'm gonna be back. So don't go anywhere. I'm gonna continue programming in Sassembly. Hello. Floor is not implemented. That is right. Okay. Yes. Okay. Now it's gonna be a to-do. Fabs is not implemented. And another thing we need to implement, we also need to implement frac. We need to implement frac. So it's going to be to do. Frac is not implemented. So this is the auxiliary function that we'll need at some point. So we'll need them. How can we implement them? So frac. Fabs look like something super easy to implement. So essentially we convert 0. So this one is pretty straightforward, right? So we essentially just compare it to 0. F absolute. So if it's less than 0, then we skip it. Oh shit, I know what it is. Yes, it's like a, yeah, we're using like a, yeah, -0. Oh my god, this is so cool. This is so cool. So essentially, do you know how you can negate a floating point IEEE 754? You essentially take -0 and you XOR it. You can actually, yeah, essentially you can flip. Yeah, so basically negation is that. Holy shit, this is actually so cool. Let me try that. Because -0 is basically 1 0 0 0 63 zeros, 1 and 63 zeros, because like there's one signed here. So, and I remember like I found that on the internet, and it makes actually pretty efficient FOBS implementation. So let me see. So in C, if you try to do something like that, right, it's going to be printf, and you have LD, it's actually LF, right? So you have 69, and you literally XOR it with -0. And then you have -69, and you also XOR it with -0. And let's see what's going to happen. You can try to compile that, main, and then run it. And it didn't work because it's an invalid operation on double. Okay, so you literally have to convert them first to you know, uints and shit like that. That looks so wrong. I mean, that's how usually it's done on a very low level. I think this is how compilers do that as well. They just XOR with -0. And C doesn't allow me to do that because of the type safety and shit like that. In assembly, it's a little bit easier. So I wonder how I can do that. So if I put these values into, like here, X is gonna be 69, and this is gonna be that. And I wonder if I do reinterpretation. If I do reinterpretation, so it's gonna be something like X, then uint 64. Maybe I'm gonna also do it like that. MZ -0. There we go. But I mean, it's literally, yeah. I mean, I kind of lost the interest in this thing, but I still want to try that. So, uint 64 result. So this is going to be that. I might as well actually do it like this. And then XOR, and I have to do it like that, by the way. Literally like this. MZ, and then I take R double. So this is how we're gonna pun this entire thing. Yeah. So since I'm doing it like that, let's actually test how it's gonna look like. std int. There we go. So I had 69, now I have -69. Right, so if I have -69, I have 69. Right, and just by XORing it with the IEEE 754 interpretation of -0, because -0 is 1, 63 zeros. And by XORing it, you basically flip-flop the sign bit. So, yeah. And this is how I do that in assembly. Alright. That's pretty cool. I'm not gonna lie. So maybe all of that panning is redundant, but if I don't pan it through the pointers, I think it's gonna be, how to say that? It may trigger the conversions by C, so I'm not sure if I can simplify this entire thing. Alright, so yeah, I'm not sure if I can simplify, so I literally have to do that through the pointer. Yeah. Because if I have double, and I literally try to do that, instead of reinterpreting double as uint64 integer, it will try to truncate it. So yeah, I cannot just easily do that. I have to do that through the pointers. So yeah. And that's why I need some sort of storage where I can take the pointer at and stuff like that. Isso. Кавай десу. Сука. Sorry. Now. So what I was doing. I'm sorry. I'm so sorry. Please forgive me. Yes. So where is this thing? Okay. So fabs or frac. What do we implement first? We implement first fabs. Okay, so we had a little bit of an educational session where we looked into how we negate stuff on a very low level. So essentially, -0 literal, is a short, like it's a single literal for 164. It's actually 63, I think. Yeah. Yeah, that's literally what it is. If you think about it. Yes. So it's basically a shorter version of 1 shifting 63. Is this a divine intellect? I think it is. Maybe. And yeah, you can actually, I think you should be able to push this kind of stuff here. Yes. Okay, so in fabs, we have we push the value and then a return, right? So that means what you want to do, you want to swap 1 and get that thing here. So after that, we want to push 0 and basically compare those things together, right? So how are we going to compare them? So it's going to be an operator that compares them like that, and if x is less, if it's less LEF, right? Or maybe greater or equal, right? Greater or equal GIF. So we have a GIF instruction, and if it's true, jump if skip negation. So it's going to be fabs skip negation, fabs skip negation, and it's going to be like at here. So if you don't want to skip negation, right? So essentially what we're going to do, so this entire thing will kill it, and that's kind of no bueno. Alright, so that means before you do that, you need to duplicate this thing here. Not even gay. Well, gay is for integers, so we're not working with integers right now. So when we're going to work with integers, we're going to do gay instruction. Don't worry about it. I think we already have a gay instruction in some places already, in some examples. Yeah, there we go. We have a gay instruction in rod 13. There you go. So it's actually double gay instruction, so we have 2 gay instructions. Perfect. Alright. Is assembly as low level as Java programming? Well, if you program directly in JVM bytecode, then I guess. Depends. Anyway, so let me see. So it's gonna be something like this. I actually wanna go through this stuff one more time. So this is another thing. I do that, I duplicate that, I push 0, then this one is greater or equal 0, then jump if consumes this entire thing, and to negate that, I think we're gonna just, you know, multiply by 1. So it's gonna be by -1. It's gonna be mult f, and it's gonna be that. And here is the result that we can just return. After that, we need to do swap 1 to put return address at the top so we can return back from this thing. Cool. So this is the fabs implementation. Epic fabs implementation. I really want to have local labels. So essentially, instead of doing that, you would put a dot in here, and it would be like a NASM. In NASM, it will implicitly add the closest not dot starting label as a prefix for this one. Right? So if you have a label with a dot in NASM, it automatically searches for the first not dot starting and just adds this prefix, and this is called a local label. Right? And this is actually pretty convenient for like labels that are related specifically to that procedure, so you don't pollute the namespace, because quite often you want to have like skip or loop or something like that. So yeah. So I think it's kind of useful, but since we don't have that feature yet, we'll have to do that manually. We have to do that manually. Cool. Doesn't even compile. So I'm gonna go to the test, and what we're gonna do here, I'm gonna push 69, and I'm gonna call fabs, and then I'm gonna native print f64. After that, I'm gonna do -69, call fabs native print f64. There we go. And let me see what's gonna happen. I keep using the wrong thing, actually. I keep using the wrong thing. Okay, seems to be compiling, and it printed 69, 69, and yeah, so we actually pushed 69, and then -69. So if we remove fabs in both of the cases, right? So we can remove fabs. It will print 69 -69. Yeah, it did. So fabs works correctly. Fabs work correctly. The sex number, yes. Sex, fugs. All right. So we have fabs. We implemented it. Wait a minute. let's try the Zorin -0 trick. Because in BASM, you don't have to do anything to reinterpret things. You can push this number onto the stack and then use beat operations, and it will automatically treat whatever you pushed as beat, so it doesn't care. So that means we can literally use this trick where I push -0 and then just Zor it, and that will do the same thing. Okay, I didn't think about that. That's actually pretty cool. Well, theoretically it should. And it did. It actually works. Yeah, I can literally do that. You can push -0 and then Zor it. That's funny. I think that's pretty cool. Anyways. We need to implement frac. How to implement the frac? Right, so frac should essentially take the number, remove the fraction. Removing fraction is actually super easy. You just have to truncate it. You remove the fraction, and then you subtract the fractionless value from the original one, and you get the fraction. You see what I mean? Should be pretty straightforward. So, okay, let's quickly do that. Now, Nuffly, hello, welcome Nuffly. So we have a value and then we have a return at the top of the stack. Cool. So the first thing we do, we swap one and we get this thing. Cool. So I think the next one we want to duplicate this entire stuff, and there we go, we have a second one. We know that it's a float, so that means I want to take the float and converted it to integer. Right, because double can be negative. We want to take that into account as well. So this is gonna be an integer now, right? Well, after that, we want to convert it back into the float. So it's gonna be I to F. So after that, the value will lose its fractional part because it was first converted into an integer and then from integer to float, so it doesn't have any fraction. And by doing -f, we subtracting that value from here, and here is the result. So it should be as simple as that. So you do this, a couple of these conversions, you subtract them, and of course after that you need to do swap 1 to get back your original value. And we actually following our pattern of accessing local variables, where you just do swap 1, do an operation on that variable and swap back. So yeah, that's pretty cool. I think that's pretty cool. So yeah, here's the fraction. So let's see how it works. So we're gonna push 69 for 20, and then I'm gonna do frac, and then we're trying to print it. And then I'm going to try to do the same thing, but with a -1. -1 should also take that into account, maybe. Because if you negate it, it will do plus, which will subtract it. Okay, that's actually perfect. Okay, frac, let's see what's going to happen. Let's see what's going to happen, and there we go. So we had 69 for 20, now we have only for 20, and for the -1 we have minus for 20 for the fraction. So we are capable of extracting fraction from the numbers. That's pretty cool, and it's actually super easy to implement. Alright, so we have fabs, frac, and the last one is to implement floor. So the floor is implemented using frac, if I remember correctly. I think. I didn't think so. Yeah, it's actually gets embedded there. But essentially, floor, you want to truncate it. Right, you want to truncate it, the original value, and also extract the fraction of the original value. And then you compare the fraction. If the fraction is negative after that, you wanna decrement the original value. So it's kind of sophisticated. The floor is not as easy as just basically truncating, right? Because if you have a floor -4201, the result is not equal to -42, right? It's not. It's actually equal to -33, because you're rounding to the lower number, and 43 is less than 42. Like, I mean, minus 43 is less than minus 42. So this is very important. It has to be mathematically correct like that. So we have to be a little bit careful with that. Whew. All right. Cheers, by the way. To be fair, implementing all of that in BASM is a little bit easier, not gonna lie. But I mean, it's probably not as efficient as in x86-64 directly, but yeah. Politically, mathematically? Yeah. So where is my stack? Okay, so in floor, we start with ret x, and of course we want to do swap. Swap 1, and this is like the scope within which we work with x. Within that scope, we can forget that return exists, right? We can just simply forget that it exists. This is actually super convenient. So once we have x, I think we can just do dupe 0. We can do dupe 0, and here is that thing. Dupe 0. You mean that not having to search for and trying to understand? Yes. Yeah. I know. Amazing. All right. So after that, I need to do I to F conversion, right? I to F. So here's what I have here. Then F to I. So this is basically how I truncate it, right? This is how I truncate it, F to I. So this is a truncated value that I should return, I suppose. But then I wanna also do a very interesting thing. What if I don't do that? It's probably going to be complicated. Okay, so we have that. So after that, I want to do duplicate 1, and that one will return this thing here, right? And I want to duplicate 1 yet again. That will give me that. Right, that will give me that. And if I subtract them, minus, it will give me the floor, right? It will literally give me the floor. But then I need to compare that floor with the original value here, right? Actually not compare it, but I need to take a look at... Oh yeah, this is the fraction, right? And if the fraction, right, less than 0, so we have to do push 0. So this one gives me 0 then, and what I want to do, I want to compare this entire stuff like so. If this fraction less than 0 or greater than equal, right, greater than equal, Jeff yet again. That means I want to skip floor skip decrement, right? Floor skip decrement. Floor skip decrement, right? And that consumes this entire thing. All right. So, and in here, actually, in here, what do we do? Push 1, right, 1, minus gives me that, right, and after that I'm done, but I still have this X that I need to actually remove, so I'll have to do something like drop, right, and this is the result, and I feel like this last drop could have been avoided. Okay, The last drop could have been avoided, but that means I'll have to look into that one more time. So last X looks like redundant, but overall I think that's a pretty good implementation. How about to split values in IP stack? That has nothing to do with the problems that I saw right now. You don't even try to understand what's the problem. So lazy backseating, that's what it is. Alright, so what do we have? What did I implement? Floor. Okay, so I'm literally gonna do floor, right? So this is the floor and this is the floor. Cool. Let me see. Okay, so the result of floor has to be 69. The result of this floor has to be 70. Let's find out. And yeah, something went horribly wrong. I don't know exactly what. Okay. So I don't really like this solution. So, and especially like this is an indicator that I'm doing something wrong in here. So I'm gonna just remove it one more time. So we know that we have an X on the top of the stack, right? We know that we have an X on the top of the stack. It does not relate directly to each function duplicates the swaps. Yes, it does. You're a very observant person. That's what I can agree with. But you're missing the point. You're not observant enough to understand the point, though, fortunately. Okay, so we have this one, and I maybe want to duplicate this entire thing. Okay, so we duplicated it, and then we do this thing, which converts it to an integer, and integer to float back. And it should actually work. Like, I don't quite understand why it doesn't work. By the way, so maybe I'm gonna just test if I understand the stuff correctly. Like, it should work. Right, so if I have 69 for 20, right, I'm gonna push it like that, and then this, and then I to F, and then native print F64, and let me see if it's gonna work. Let me see if it's gonna work. Okay, so it does actually, you know, the thing. What is the language? It's called BOSM. It's an assembly language for a virtual machine we're developing. All right, so you can put it this way. It's our own programming language. So yeah, technically it is true that this is our own programming language, but it's just an assembly for a bytecode of the virtual machine that we implemented. All right. So yes, basically that's what it is. If it makes any sense, I'm not sure if it makes sense. Cool. So yeah, it's not that big brain, to be fair. I think I have a boot. Nice, congratulations. Very epic. So what I'm thinking is that maybe we have to duplicate 0 this thing. All right, duplicate 0 one more time, like this. And maybe swap 0, 1, 2, swap 2. Right, so, and once you swap these things like that, you have this result, and then you do minus f, you do minus f, and you get the fraction. So yes, this is perfect, I think. Now, what we can do, we can push 0. We can push 0, and then we can compare if it's greater or equal to 0. So this is what we're gonna have, greater or equal to 0. Right? And if it is, that means we need to skip the decrement. Floor, skip deck, floor, skip deck, and within that thing, 1, 2, 3, 4, we're gonna do, so of course this entire thing, you know, consumes it. I'm gonna push 1 on the stack, then we do minus, and that decrements 1 from this entire thing. Not 11, but 1. And I guess that is all right. That is all right, after which we can return back. Yes, that's actually way better implementation, I think. I think it's way better now. Yeah. So that's pretty cool. I especially like this pattern, like. And in the future, when we're gonna have like a more powerful macro system, so maybe we'll have like blocks and stuff. Alright. Cool. So let me go to the test bosom. So minus 69 minus that, and let's try to run this. A legal instruction access. That is very interesting. Did I forget to halt? No, I didn't forget to halt. Okay, so something went horribly wrong. That's very strange. Floor skip deck. Jump if. Jump if. That's why it's actually did wrong like thing. But I mean, it shouldn't be that dramatic. So it's okay. Okay, it worked, but it never actually. Okay, it's an opposite thing actually. Jeff. So greater equal. That means it has to be less than. I think. Yeah, there we go. So that's correct, I think. No, it's not. Yeah, it is correct. All right. So this is correct. This has to be 70. But there is another thing that we need to test. Minus 69 and trying to floor this thing has to be still minus 69, right? Because there is no thing to floor. It's already sort of like whole number or integer. Let me see. So that should work correctly as well. And god damn it. Okay. So it has to be 69. So maybe it has to be less than or equal than 0 then. We can try that one. And there we go. So we have 69 minus 70 and still minus 69. Floor has been implemented correctly. There we go. That's pretty cool. That's pretty cool. Yes. Okay, so here's the floor. So I think we implemented all of the functions that we needed: fabs, frac, and floor. Then we have B, and the time has come to implement print frac. Now we can implement print F64 entirely in the bottom. Yes, that's exactly what we're gonna do. That's exactly what we're gonna do. Ooh. I'm sorry. Yeah. So we have R, M, and U. I'm not sure what U is initially equal to. So what? And then U is just saved. U. It still needs to be used for something, but replacing that U all the time is kind of a weird thing. So we recalculate R. By the way, this one is sort of like a mod. I forgot what it is. X mod 1. The fractional part of it. Okay, so this is the fractional part. This is a floor and this is a frac actually. I keep forgetting this is a floor and this is a frac. Makes sense. Floor and frac, and this is just a regular multiplication. Okay. Okay, you're welcome, roll 008. You're welcome. I actually gifted a bunch of subs, so yeah, you were a lucky one. So, congrats on getting the sub. Okay. So it was completely random. So yeah. Okay, print frac. So what do we expect here when we print in a frac? let me see. We have a return address, right? We have a return address, and at the top we have F. How does offline gifting actually work? Completely random. It's not really offline gifting. It's like generally random gifting. I don't think it like being offline or online affects it somehow. So I think the criteria is a secret. So Twitch basically uses the activity of the users, and based on that activity it gives more chance for a random gift sub. But what's the criteria, what's the function? I think it's a secret. So they take into account for how long you've been watching, how active you were in the chat, and so on and so forth. Like they take all sorts of criteria, and maybe that contributes to the final, you know, decision on gifting the random sub. So it is very needed to prevent like gifting subs to people who don't care about the channel, right? So yeah, you want to gift subs to people who do care about the channel. So you need some sort of criteria. I'm very active in the chat though. Do you use Chaterino? I think maybe using Chaterino actually affects that, so maybe they don't count Chaterino user. I don't know. Once I got gifted a sub for a channel I viewed for a total of maybe an hour. Yeah, there's definitely a stochastic element to that, I'm pretty sure, but I don't know for sure. I got a gift sub on a random channel which I don't even watch. Well, maybe it was a long time ago. I think they're constantly refining that function. Alright, anyway, so we need to do swap 1 and swap 1, and that essentially eliminates 1, 2, 3, 4. It essentially eliminates the return function, so we don't have to worry about it. It was yesterday. Well, that does not contradict to my statement. Anyway. So we have F, so this is going to be original thing here. Then I'm going to push, I guess, N, which is going to be frac precision. So we have a frac precision. And after that, I have to call to B. Right, once I call to B, this entire thing will be BN thingy. Right, so we have a BN thingy. After that, I need to divide it by 2. So I'll have to push 2 and then div. Okay, so push 2 and then we do div, and that is basically half of that. So there we go. We have R, we have M, which is B to the power of -1 divided by 2, and we are good to go. So let's do print frac loop, right? Print frac loop, and here we also have a condition thingy. Jump print frac loop. There we go. So this is the loop. So by the way, this kind of, like, I was complaining about this loop at the beginning, but I realized that this kind of loop is so easy to translate to assembly, right? Because it's just, you know, just an unconditional loop, but with the condition in the middle to break out of the loop. And in assembly, it makes it so easy to implement. All right, so what are we doing here? So, and this thing actually could be called M, and this one could be called R. So I think I'm gonna keep them like that. Oh, Cozy White Bear, welcome to the stream. Hello, hello. 1, 2, 3, 4. So now we need to do U. To do the U, I need R and B. So R is gonna be dupe 1, right? So this is a dupe 1, it gives me that, and B is 10, so that means I can push 10 like this, and after that I need to multiply them. So I do mult F, that multiplies them together, and then I need to take the floor of them. So it's going to be call floor. So this is going to be a floor of that stuff. Cool. So we have that. That's pretty pogue. Not gonna lie. So, and by the way, the initial state of the loop is MR. So this is the initial state of the loop. Initial state of loop. It's MR. Hello, Rodriados. Welcome to the stream. Okay, so after that, we need to update R. We need to update R. Updating R should be interesting, right? Because you can always do it like that, I suppose. Swap 1, swap 1. Actually, it's not swap 1. Wait a second. Did I do a fucky wacky? No, I didn't do a fucky wacky. It's still dupe 1. Okay. So in this particular case, R is going to be the second one. So it's going to be swap 2, and that essentially lets me like work in terms of this variable. 1, 2, 3, 4. And what I want to do here is I want to actually... Ivanchuk, thank you so much for 2 months of Twitch Prime subscription. Thank you, thank you, thank you. And welcome to our epic Key Comrade Club. Yeah, so essentially, I think I already explained how to read this nickname. Yeah, it's basically written in Cyrillic, but using Latin. Yeah. Right, so what I want to push here, I want to push 10, right, to here. So it's going to be 10. And then we're multiplying mult f. So it's going to be like that. And then we need to call the frac. Call the frac, and after that we're doing swap 2, so that means it brings it back here. So cool. So we updated that one, and also we need to update the m. So it's going to be similar, swap n, swap m. 1, 2, 3, 4. Push 10, just mult, and that's it. So yeah, that's pretty poog. After that, we need to probably, so that gives me like this, so it's going to be multiplied by 10. Cool. After that, we need to check this condition, right? So we literally need to check this condition. How can we check that? Print frac loop break. There we go. So this is the break in the loop. Okay, so this one is M, and this one is R. So that's what we know for sure, and this one is U. This one is U, poke U. And so we'll need to have these conditions here. So we need to take R and M, so that means we'll have to dupe 1, 2 is going to be 1. So by duping that, it gives us that. And 1, 2. No, not really. I have to dupe 2. 0, 1, 2. That gives me R. That gives me R. And then duping it one more time gives me M. Right, it gives me M yet again. And it gives me that. Okay. Then when I'm comparing them, right, when I'm comparing them, I actually compare them like this. Right, but maybe it would be better to put it like that. So, yeah. Yeah, when I do comparison operation, they're actually compared like this. So I probably have to swap them. Swap them like this, and that will make the trick work. Then I can do greater or equal Jeff, right? So that means greater or equal. Greater or equal. And if this is true, break out of the loop, right? Or no? Actually, we need an opposite thing. I think we need an opposite thing then. So an opposite thing is going to be like this thing less. And if you swap them around, it's going to be actually this. If is less than, okay, so this is very interesting. Let's try over, but for that one specifically. Okay, so I'm duping 2, so 1 2, so that means I duped R, and then I'm duping a 2 yet again, so that means it dupes M. Cool. We want to break out. We want to break out when R is actually less than M, right? When R is less than M. So that means if I put it like that, that means I have to put something like less than F, right? So by doing that, I have that, less than. And if I, then I can do jump if, printf break, so this is that. And that consumes this condition, so which is perfect. Okay, that's super nice. Now, I need to do a similar thing, right? I need to try to dupe that one more time, so that dupes me R, and then it dupes me M. So I have R and M. Are we winning? Yes, we're winning, don't worry about that. Everything's okay. So after that, I need to subtract 1 from it, but I have to do that slightly differently. So I'm pushing 1. Right, so, but if I try to subtract it, I will subtract 1 from here, but not 1 from M, so that means after that I need to swap 1 by doing it like that, and if I do minus F, I'm gonna be subtracting this thing from here. Cool, so that prepares that condition, this condition, so okay. And when do we want to break out? R has to be less than its value, so that means it has to be greater. So what we're trying to check here is if this thing is greater than that one, so that means it has to be Jeff. Actually not Jeff, but GTF. Right, and then jump if print frac loop break. So there we go, so we check this condition and we ended up with this thing. Afterwards we have U, which is a number, right, which we need to print. So how are we gonna print that thing? So first of all, I think we need to convert it to an integer, or rather to unsigned integer. So it's gonna be f2u. Alright, so it's going to be f2u, and that is just a single number. Then I need to push 0, right, so it's going to be just 0. Happy Wednesday, thank you so much. Push 0 and then do plus u. Do I have plus u? Oh, it doesn't matter, we have 2's complement, I can just use this one. So it's going to be that, and I have a character that is in ASCII printable on this screen. That's what I have here. I have a thing that is printable on the screen. So what do I need to do now with that? I need to print it using write. So maybe I have to put it to the memory somewhere. Well, ideally it would be nice to first put it. Yeah, it would be nice to put it on the screen, but let's try to do that one character at a time. Right, so after that I'm gonna push print memory, right, so I'm pushing print memory, and the memory has to be below the value that we're pushing, right, so that means after that I'll have to do swap 1, right, so that's the more or less correct value. And then we do write 8, because I'm pretty sure it accepts first the place where you want to put it and then the value. So that essentially consumes that literally consumes that, and then we want to do a write syscall. So I'm going to push print memory, then push 1 because I want to print a single character, and then I do native write. Right, so in that prints that character from the memory. And after that, I think we finished a single iteration of the loop. We ended up with M and R, and this is exactly the initial state of the loop. This is in exactly initial state of the loop. All right, I think we finished the loop. Holy shit. Okay. Now, so after the loop, we need to check additional condition, right? So, U. Oh yeah, if we break in the loop somewhere here, if we break in, okay, so we're actually wasting U a lot of times. All right. So here's the last condition. And I'm in over SSH. Nice. You're doing FreeBSD on Pi, right? If I understand correctly. Okay, so here's that. Here's that. If you break, you will have a U. And somewhere here, we probably want to actually duplicate it first before doing anything with it, right? So we want to duplicate it first. Right, so let me try to do dupe 0 and only then do all of that nice stuff. Right, do all of that nice stuff. But do we need to do that? I don't think we do need to do that. Yeah, I see. I see. So basically, once this condition hits, we're gonna end up with U because we didn't process it here. Okay. So at this point, we have UMR. So that's quite important. We have UMR. And what do we need to do? We need to take a look at R, and I think we can literally just do swap 1 2 to bring R in here. All right, then we can push 0.5 onto the stack, right? All right, so what's interesting is that there is like 2 conditions in here. So after that, we only want to increment Y if R is greater than half. R greater or equal. Alright, so that means we still have to use Jeff one more time. So this is what we get here. Right. And we actually want an opposite. We need to skip +1, right? So that means we need to do LTF, right? So we need to do LTF. Okay, so that means after that, GMP print frac skip increment, and we do print frac skip increment. And in this particular case, though, this entire thing has been consumed, by the way. This entire thing has been consumed, and we need to do push 1 plus f, right? So that will increment it by 1 if it's needed. And in here, we need to print that entire thing yet again. So how do we print it? We just convert it to integer and save it to the memory, and then we print it. This is how we print a single character here. So, yes, so I suppose. So it has to be like that. So, and that lets us consume that thing. And after that, we only have M on the stack, which we want to simply remove. Right, which we want to simply remove, and we're gonna just drop that. And I think, I'm not sure if we want to do swap after that, right? I don't think it has to be swapped after that, because return is going to be naturally there, so no swappage is required. So that means I'm going to put it like that, I suppose. Alright, so that's pretty fat function, not gonna lie. And so and then we return. Okay. And maybe it implements the algorithm, maybe it does not. We're about to find out. So does it compile? Does it even compile? Let's find out. It compiles. So test. Well, I mean, it gets included everywhere. It's just a fuck around machine. Yeah. Oh, I see. You're talking about your Pi. All right. So that's pretty cool, and I wonder if it's gonna if we're gonna first try this entire thing. I wonder if we managed to first try it. So let's take a look at the test bosom, and so the thing about printfrag, by the way, the thing about printfrag is that it accepts only values less than 1. So we'll have to push something like you know, 69 for 20, whatever, and then we have to call print frag, and what it will do, it will print 69420 and so on and so forth, right? So it will only print the fractional part, hopefully. We'll see how it goes. Alright, so let's try to compile this entire stuff, and if I try to run it, it has an illegal instruction address. Okay, so that was really stupid of me to think that it's gonna work first try, of course. Alright. So we'll probably have to debug that. We'll probably have to debug that thoroughly. Yeah. So maybe we're gonna go through this entire machine trying to understand what the hell is going on. So yeah, not first try. Yeah, not the first try, unfortunately. Okay, so here is the thing. So we have 69 for 20 and then a return address on top of it. Cool. So what we do here, we swap them around and then we push frag precision, right? We push frag precision and then we call B. Right, we call B, and that consumes the frag precision and puts a B minus N thingy there, right? Then we push 2, and then we divide by 2. So this is basically what we have here. Cool. Now, so here's the loop. We duplicate 1, then we add 10, and then we multiply it by 10. Cool, we multiply it by 10, so, and that basically shifts the point here, and then we call floor, and floor just gives us 6. This gives us 6. Cool. Swap 2, 1 2. So we swap this around like this, then I do 10 and I multiply it by 10 yet again. I multiply it by 10 yet again. That gives us that, and I take the fraction of it and I swap it back. So yeah, that makes sense. So far that makes sense. So this one could be something like, let's say 0001, right? It doesn't really matter. So I swap this thing around and then I do 10. So we're gonna do 10, then we multiply it by 10, right? Multiply it by 10, that decrements that thing one more time, and we put it back into its place. Okay, then I duplicate this thing 2 times. Actually, this thing. Duplicate that. Duplicate that. And then, if this thing is greater than that, then we break out of the loop. So I think the condition is broken somewhere here. So the condition is broken somewhere here. And I'm not really sure. So let me see. So it was originally something like this, right? And we do less, so it has to be less than. If this thing is less than, we break out of the loop, which is not correct. So I think it has to be greater than. If this entire thing greater, whatever we have, then we have to break out of the loop, probably. Probably. Alright, so we do that thing yet again, so it's gonna be dupe 2, dupe 2, dupe 2 do 2, then we do push 1, right, then we swap them around, and then I do minus, right, so minus, and that gives me 0.99999 something. Okay, then I compare it, so greater than, greater than, so if the value somehow greater than, Maybe that one is also correct. So I think this was somewhere here. This was somewhere here. All right. After that, if we manage to fix that, so we convert it to this thing, then we add this thing here, then we add it. We put print memory, right? We put print memory, and of course we swap it, and then we push it to the memory. Right, we push it to the memory, then we push, yeah, then we push the memory one more time, then we push the size and we write it again, and then we continue. So at some point after the loop, we're gonna end up with something that has U, right, with something that has U, and this is what we'll have to do. Okay, so I think the problem was primarily somewhere here, I think, like around, if I understand the algorithm correctly. I might be not understanding it correctly. Alright, so if I try to run, yeah, it was not correct understanding of the algorithm. It would be nice to know where exactly it failed, somehow. Maybe we could extend the virtual machine to like have debug information and tell us where exactly, like have some sort of like a source maps. Illegal instruction access, as far as I know, where does it happen? So let me see. Illegal instruction access, it's when you go outside of the... Yeah, so it's when you go outside of the program, usually. Like it's literally like when IP becomes bigger. And I'm not quite sure why it would do that. When you will update your avatar to bold one, I don't know. So test. So it usually happens when you forget to halt, right? But at the same time, it might be because you forgot to return, or maybe it returned into a completely different place. Okay, so let me actually put something here. I'm gonna put debug here, and I'm gonna try and recompile that. I think that's basically what's going on here. So if I go to BDB mode, right, I'm gonna break on debug, and I'm gonna just run this entire thing, and it printed only 0, right? And let me take a look at the stack. So in the stack we have this thing, I think, which is not particularly correct in my opinion, alright, because at this point we should have only return address. So right, if I try to return that, okay, so it's segfaulted. That makes sense. So it couldn't actually jump there. So that means our return address was completely incorrect somehow. Well, I mean, it's segfaulted because you don't check for overflow of the IP instruction. Don't worry about it. So that makes sense. Yeah. So the address is not correct. Oh yeah, okay, so this is the last thing here. And I think what I forgot to do... Yeah, did I forget to do another drop? Because this is the top of the stack. Yeah, probably. It's not the problem right now. I feel like I need to drop another one, but I'm not sure. Yeah, okay, so I basically have an incorrect value. All right. Oh, I need to start over. So yeah, I need to start over because this one is, yeah. It's hard, man. It's fucking hard. But if we manage to pull that off, it's gonna be very fucking cool. We can try to BDB one more time. Okay, so I'm gonna break on main and just run it. Okay, so cool, and we go in there. So here's this stack. So this is the return address, and this is the input value. So we have that thing. Next one, we push. Okay, we swap them around. We're gonna push 6 there. So 6 was pushed there, so because it's that. And then we are about to call... Oh boy, I really miss the feature of skipping over the calls. This is very important feature. It actually, oh my god, no. Well, to be fair, maybe it's not that bad of a thing. So essentially you can break on main, right? You can break on main. Hello, XXDVXX. So you push that and you, okay. You're about to call. You can take a look at the IP and you can break at 13, right? So you can break at 13 and then you can continue. Oh, it's already running. Okay, so I see. So this is essentially what we can do to negate it. Okay, break, run. Okay, we're going into swap 1, push 0, call, and I'm gonna take a look at I, break 96, continue. And after that we have this value. Okay, so that's kind of cool. Next thing, we do the division. Really? Oh yeah, so we pushed 2 and we need to do the division. Cool. So after that we divided it by 2, but did it really divide it by 2? I don't see it being divided by 2. Excuse me. This is not divided by 2. Holy shit. Wait a fucking second. That was not divided, wasn't it? Excuse me. So if I push like frac precision, then call B, then push 2, and then say div f, and then do native print f64. It should give me the half of that stuff, but it doesn't give me the half of that stuff. Okay. It doesn't give me that. What if I make the precision a little bit smaller? So I think I found something really weird. Maybe we need to make the precision a little bit smaller. Maybe something is really bad going on. Okay. Let's make the precision like 5. Sure. Maybe that's going on. Like, oh fuck. Okay. BME. Okay, cool. So maybe after that, shut is that. Okay, so it doesn't matter. All right, I see. We need to start over. We really need to start over because I fucked up that one. So let's go and start over. So let's find return. So here's the return, and let's push it here. So this one is a little bit complicated. So the algorithm is complicated. So we need to be a little bit careful with all that. Oh shit! I want to make a small break. Does anyone have any questions? Yeah, right now, because I need to like really get my mind away from that thing. How everyone is doing? Is everyone working right now? Today is Wednesday, right? So that means today everyone is working. I'm working every day, so. So what are you guys working on? You're working on something interesting? Work. Yeah, it is what it is. Watching. Is that your work? Are you from KGB? Are you my personal KGB like agent that is, you know, watching me and following me and stuff like that, making sure that I don't do anything like bad? Working and staying alive. Nice. Also work with coding background, I see. You're coding in PHP, I see. Trying to understand why my Ignite doesn't send events I need. Yeah, relatable. Relatable. Oof. Yes. Python coding mostly. I see. What kind of Python? Is that web development or data science or something? Rustlang. Somebody's actually unironically programming in Rust. Or is that for your job? Are you getting paid for programming in Rust? Ruby. Oh, I know that you're doing Ruby. Like you were doing some sort of DNS thing in Ruby. Personal project, I see. No, it's also good. Personal project's also good. Alright, so I'm gonna quickly go to the kitchen. I think I wanna drink some water. Okay, I'm gonna be back real quick. Just a second. Hello, welcome back. Alrighty. So. Wait, really? Did they really make it a PogChamp? Seriously, Twitch? Okay. Yeah, that's very funny. That's a very funny joke, Twitch. Ha 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 ha. I see. I mean, maybe I guess maybe that counts as a PogChamp. I don't know. Whatever. I have a pretty interesting idea of trying to develop this thing. So what if we constantly maintain a debug label, and after writing a little bit, we can go into the debugger and just check how it works and stuff. So that actually sounds like a very interesting idea. So this is what we do here. I'm going to recompile everything, and then I'm going to go to BDB. I'm sorry. So this is going to be like that, and then I'm going to break on debug, and I'm going to just run it and take a look at the stack. So in the stack we have the value, the fractional value that we put there, and the return address. So that means the first thing we have to do in here, we have to swap it. So we have to do swap 1. Right. So we might as well actually do a very interesting thing where I do build sage. 69 420. Okay, then I break on debug. I just run it, and if I take a look at the stack, okay, so that was swapped successfully. And in here, maybe it makes sense to maintain the stack. So initially, what do we have now? We have the fraction here. We have the fraction and the return address after the swappage, right? After the swappage, it is like that. So we already initialized R, so this could be R, and we need to push the precision, right? So it has to be frac precision. We're pushing it there, and then we call in B. So that should give us the BN thingy, right? It's going to be BN. And let's try to test it out. So I'm going to kill that, and we're going to do bdebug, and I'm going to run it and take a look at that. So essentially here, as you can see, we have this small thingy. After that, we have to push 2. So it's going to be 2, push 2, and then div f. So that will divide it by 2. And then I'm going to try to recompile that. I think I didn't properly recompile it one more time. Alright, I'm gonna break on debug, Then I'm gonna run it and take a look at that. So we have half of that. Very important question. Does it feel best when you're completely bald or when you have a bit of stubble? To be fair, I think it feels for me better when I'm completely bald and I can feel my skin. I like it a little bit better. But at the same time, you have to be really careful because essentially you have exposed skin on your head, so you have to take care of it as much as any exposed skin. Is this printing a float or just a fraction? Right now a fraction, but then it's going to become a part of a bigger function that prints the float, right? So printing a fraction is only part of the better printer, more complete printer. Currently I'm in uni and not choose for specialization yet, which is more benefit to choose software engineering, data science or cyber. I'm confused. I don't know, it depends on how the industry will go. I don't know. Right. So you may choose, for example, data science, and then in 5 years, the data science is not going to be trendy anymore, and all of your skills are going to become useless, and you cannot predict that. You cannot. That's the rules of the game. That's the rules of the game. You have to choose something. You have to gamble, right? Or maybe not. Maybe it doesn't fucking matter. Think about that. So if you like what you're doing, right? If you like what you're doing, does it really matter if the market needs that or not? I don't know. Here's the thing. Okay. I think trying to predict what the market needs in the future is a wrong approach because you can't predict that. What is better? And you know why it's also bad? Because if you're just trying to pander to the market, you may end up actually earning a lot of money, but at the same time, you may end up doing what you don't like 8 days, like 8 hours a day, right? So, which is also a problem. So first of all, you cannot predict the market. Second of all, if you are lucky, you may end up doing something that you don't like for like 40 hours a day. So let's actually put it upside down. Let's actually try a different approach. Let's try doing what we like. Right. So we start with the base. We're doing what we like. And once we established what we like, let's think how we can monetize that and how we can embed into the current market. That way, we end up doing what we like, and we don't have to predict the market. So we already have the thing that we like to do. We look at the current market, and we just try to embed there. So we don't need to predict anything, and we do what we like. Does it make sense? It makes sense? I know that it's difficult, but I think it's like an opposite approach. Okay. Love it. I was not saying about love it. It's all about definitions of the word. Okay, so we're going into weird discussion. All right, whatever. So we have that, and after that, so this is M and R. So this is M and R. We need to start the loop, right? So it's gonna be print frac loop, print frac loop begin jump, and it's always gonna be unconditional, and the end is gonna be somewhere here. When discussion turns into arguing about definitions of words, I really lose interest instantly. So, and this is exactly the case. Cool. So we have that, and I think we'll have to put the break somewhere here. 4. Maybe use less vague words than love. Yeah, it's as simple as that. Yes, yes, yes. Sure. Holy shit. Okay. Just use less vague words. It's that fucking easy, dude. All right. Holy fuck. So R. So it has to be like 0, 1. It's okay. Dupe 1. Just get a house. Just get a house. Dupe 1, and we need to multiply it by 10, so it's gonna be 10. Let me actually try this thing like that. So it's gonna be 4 values. Oh shit. And now it's just the problem is that people don't understand the phrase depends on definition. Like they literally don't understand what that phrase means. Hello, Sanjay Tugor. Hello, hello. So yeah, and they end up in that trap of discussing definitions of the words instead of discussing the matter, right? So you discuss in the matter, and then you fall into the trap of discussing the definition of the words. And majority of people are incapable, like I think mentally incapable of getting out of that trap, even if they're told so. Even if they're told you're in a trap of discussing definitions of the words instead of discussing the matter, they're incapable of getting out of that trap because they don't see the difference. For majority of the people, there is no difference between just discussing words and discussing the matter. Right, and even if you tell them, get out of there, they cannot, they don't understand what you mean, because it's the same thing for them. So, yeah, essentially, ideally, it would be nice once the people realize, okay, we're not discussing the matter, we're discussing words. Let's establish what we mean by these words, and we use these understandings and definition within that conversation to discuss the matter. And it takes a lot of mental effort that not a lot of people are capable of doing, unfortunately. And that's why, by the way, majority of political discussions are shit, because you easily fall into that trap as well. So, anyways. Alright, so I'm gonna do R, and let me take a look at this text. So I have 4 values, and this is exactly the stuff that I have on there. So that's pretty predictable so far. Okay, I put it there, and then I want to push what? I want to push 10, right? So I want to push 10 and break and debug, run, and here we go. I have 10, and after that I have to multiply all of that. It's going to be multiplied, right? Break debug, run, and we multiply this entire thing, but afterwards we have to apply a floor in it. All right. Apply floor in it, and we're gonna run it, and here is the floor. So essentially we extracted that single number out of it. So in that case, so it's gonna be f multiplied by 10, multiplied by 10, and floored, and in this is UMR. What's that supposed to mean? So you have a UMR. So here you calculated U, right? And that's pretty poog. And this is the digit that you have to print if everything is okay, of course. Alright, so let's start with updating R. So 0, 1, 2 is going to be swap 2, and that brings this thing here. Right. Then you push 10, excuse me. What the fuck? we push 10 and multiply this thing by 10. There we go. So you have 10 multiplied by 10, and then I think this is the fraction, if I remember correctly, right? So we use the notation x to mean x mod 1, or the fractional part of x, the fractional part of x. So that means I have to do it like that. So we're gonna call frac. So, and yeah, this is gonna be just a frac without like a single thing there. All right, so if I try to put it here now, break debug, one more time, break debug, run, and stack. Yes, so we actually, so there was 69 for 20, now we have 6 here, and 9 for 2 is in the last, like in the last fraction here. So, and then we can swap 2 back, right, and bring m in here, so that makes more sense now. All right, so here we're gonna have 6, and then we're gonna have the rest of the digits here, and this is gonna be this weird thing at some point. Okay, so let me recompile. I didn't really want to recompile that though, but yeah. Break debug, run stack. So here is the 6. This is the small thingy, and this is the rest of the digits. So far, so good. So far, so good. So the next thing, we need to update m as well. So that means we'll have to do swap 1. So that will give me that. Then swap 1, push 10, actually not 1 but 10, right? And then multiply it by that thingy. Right, cool. Oh shit, Emacs. Okay. After that, so I just want to see that it got incremented. That's the only thing I want to see. And let's just run it, and yeah, it got incremented because 5 was actually here, so perfect. This is actually a pretty cool way of developing in Bosom. Essentially, you just maintain this label, debug, and yeah, what is Hasm? Hasm is basically a header for Bosom, things that you include in other Bosom files. So, for example, here, I include that file for a standard library. So that's what it is. Bosom is like the program, and Hasm is something that you include. Cool. I'm really glad. That's very funny. All right. So after that, I do swap 1 yet again, and this is what we have here. Cool. UMR. After that, we need to check all of these conditions. All right, so we need to check all of these conditions, and did I save everything? What is UMR? Is that new kind of UML? Hello, Jiang. Hello. It's a parameters of the floating point printing algorithm. We're finally implementing the printf64 in Bosom. And these are just the variables that are used by the paper to denote different values. So U, for example, contains the digit, the current digit that you want to print. R contains the rest of the fraction that you're printing. And M contains the, I think it contains the precision, right? I think it contains the current precision, and you actually increase the precision as you print more and more digits. Actually, you decrease it by like moving closer to the period, right? And so these are the values. This is the digits, this is the rest of the fraction, and this is like the current precision or whatnot. Yeah. So, and that's kind of interesting, actually. You stop when the current fraction that you work with goes outside of this range that is defined by your precision value, right? So if it goes outside, you break out of the loop, essentially. That's right. Okay, so we updated all of these things. I want to actually take a look at them in the debugger logger. Break debuggers, run debuggers, and there you go. So here's the current digits that we want to print. This is the precision, and this is the rest of the digits. So we had 69 for 20, right? 69 for 20. So here's the first digit, and 9 for 20 is the rest of them, and this is the precision that we keep driving. So it's quite important because you don't really know if you have that 0 here. And this is the job of the precision, to indicate that yes, 0 is part of the digits that you're trying to print. So that's why this thing is here. So, and it all makes sense actually. It all makes sense. That's a very interesting algorithm. So you basically just iterate through the digits in the fraction. Yep. So, and this algorithm makes an interesting assumption. You, of course, can have errors due to operations on floating point numbers, but because of the precisions, you can assume that all of the errors are going to be happening after that precision. So we're using this precision to basically cut out any errors after the digits that we intend to print. So, and usually it's a right assumption, and it works. Now I understand. Yeah, it's actually a pretty cool algorithm. So as you can see, so this indicates that after that digit, just ignore everything, whatever the fuck you have here. So you may have some fluctuations here. Ignore that. It's whatever. So, and you iterate that, and you just increase it and just print numbers and stuff like that. So yeah, and the algorithm is called finite precision fixed point fraction print out. So, or FP. So there's also, yeah, you can find a paper on that actually in the original thingy here that they have. Yeah, FP, yes. Triple FP, right? By the way, as far as I know, it's the simplest and dumbest algorithm for printing floating point numbers. And I think it was invented by Knuth. Yeah, it's actually from Knuth's book. Yeah. So it was described in early drafts of oh, okay, whatever. So this is it in Knuth. So yeah. So Knuth is actually famous for his books, and his books are famous for the fact that nobody reads them. But if you read them, you probably, if you read them, you probably would discover this algorithm there. Imagine like writing shit ton of like thick books, becoming famous for that, and nobody reads them, of course, because they're too thick. It's just like the whole, your entire career, your entire life is TLDR. Yeah. Nice. Anyways. Thick books. Yes, if you know what I mean. Alright, so after that we just have to check this condition. So this is the rest of the stuff and the precision. Okay, let me actually dupe them. So I'm gonna dupe M, so it's gonna be dupe 1. Actually, maybe 0, 1, 2. I'm gonna dupe 2. Right, that will give me the rest of the fractions, and then I'm gonna dupe 2 one more time to get that thing there. So it's gonna be R, R, and M. So that's what we're gonna have. Cool. So and R. So let's rebuild that and break on debuggers. So let's take a look. So at the top we should have the precision, here it is, and below that we have the rest of the digits. Cool. So we want to break out of that loop when the condition happens. But when the condition happens? So I think I'm gonna steal some stuff from here. If R less than M, break out of the loop. Okay, so that's actually pretty cool. R less. So we can do something like this. So that's actually perfect. Less than. So that means Alt LTF. Okay, so this is LTF. And let me see if it's gonna work or not. Break debug. It is false, which is perfect. And then I'm gonna do jump if. So where's the break loop? And we're gonna put it here. Hello, Kira Race, welcome to the stream. Okay, so this is the first condition that we checked. So I can put something like if using I3. No. I'm using i5. Aha! Got him. Alright, so if r less than m, break. There we go. Okay. Cool. Classic, am I right? Classic. So this is another condition that we need to check, by the way. So, all right. So let me double check that after all of that, we have 4 values on the stack yet again. So it's going to be debug, then run it, and yeah, 4 values. 1, 2, 3, 4, and everything is okay. Cool. So I'm gonna be duplicating them one more time, right? So that should give me R and M like that one more time. Might as well actually do it like this. So on the top I have that though. So after that I want to push 1. Oh my god. Oh my god. I'm actually hungry. Break debug. So we have 1, right? 1, and then we need to subtract all of that. So if I do minus f, I'm gonna get this thing. Minus f. Oh shit. Should be a little bit more patient. Okay, so... Oh shit, this is actually incorrect. Okay, this was a good idea to test it out, so because I have to do swap 1 to swap them around, and I could have actually noticed that. Okay, it doesn't have to be negative, like it... yeah, so the debugger is super useful. By the way, Hotzenpot, thank you so much for developing this debugger, it's super useful. It's not perfect, but I mean, yeah, for developing complex algorithms, it's just, I guess it's just must have. And this approach of like having this debug thingy at the end of the algorithm is pretty useful. All right, so debug, and I really like this meta of like maintaining the debug flag, the debug label. So let's just run it, and yeah, we have this, right? We have this thing. And when we're breaking, when our R becomes bigger than this precision, which it is not right now, but maybe it will. It feels so cool right now. Yeah. Okay, so after that, if I do something like this, so it has to be GTF, right? So it has to be GTF, and it has to be false currently. Right, it has to be false, so let me see if it's false now. It is in fact false, so, but if it's true, we'll have to jump out of this thing. Okay, so we're done with this condition. I'm digging through some LaTeX at the moment, such a pain. Oh, I can imagine that. Alright, so, after that, at the top of the stack, we have a very important thing. At the top of the stack, we have a very important thing. So we have 6, and this is what we need to print on the screen. LaTeX. Do I pronounce that correctly? I think I pronounced that correctly. Should be easier for Slavs to pronounce it correctly. Okay, good. So what we're gonna do, we're gonna convert f to I. So we convert it to integer. Debug, and we do have 6. There we go. We do have 6. Well, after that, I need to push 0 and just plus I guess. Yeah, let's do plus I. My throat is dry because I tried to pronounce it LaTeX. Need some water. No, comrade, you need some vodka. Sorry. Alright. Break debug, or there we go, and now we have 54. Alright, that's pretty cool. then I need to push print memory, right? So oh, company kicked in and showed completion of keyword. Good job, buzzer mode. It's not that. Okay, so company uses as one of the sources for the auto completion the tokens in the different files. So yeah, I guess. Yeah. So basically it just knows that I have these tokens in the current file and just tries to autocomplete them. So it has nothing to do with the like company mode or anything. So it's just company mode has like a lot of sources for auto-completion and it's just one of them. All right, so at this particular point, what do we have? We actually have this as a character. So yeah, this is this thing as a character. And what I need to do, I need to print memory. So I'm pushing print memory, and I think let me see what we're gonna see in the debugger. So first we have to see character and then some memory, right? And so this is the memory and this is the character, but we won't be able to write it into the memory. Yeah, I never used company. Well, it's a very popular auto-completion framework. So it defines the framework, and then with additional extensions, you can add more sources for auto-completion. So that's how it works as far as I know. I don't really use it that often, I just have it, and sometimes it kicks in and just does its own thing, but I couldn't be bothered, to be fair. Okay, so let me try to swap this entire thing, right? Yeah, it's like Helm. Have you heard about Helm? Alright. Yeah, Emacs Helm. Oh, for fuck's sake, what the hell is going on? Shit. My asshole. That is very strange. Something is really wrong right now. Don't know what. Oh shit. Oh fuck. It's really strange. Alright, just a second. Yeah, there we go. So it's this thing. Cool. Whatever. What was doing? Imagine blocking. Well, you haven't done enough open source development to actually start blocking people on GitHub. I've done so much on GitHub. I've been on GitHub for so long and I've done so a lot of things that at this point, I'm actually have to block people. So yeah, it's a very interesting place. Yeah, I was shaving the yak. Yes, that's what I was doing. Debug, run, then S. So yeah, there we go. I have a character, I have that. And what I need to do now, I need to write it into the memory. Hopefully that will do the trick. And I need to make sure that I'm writing it into the memory correctly. So the character is in hexadecimals 36, which is nice. All right. Break debug, run. So on the stack, we have 3 values because we printed everything into the memory. And now let's try to inspect the memory. So 0, 5, and here it is, 36. Here is the character. Nice. After that, what I want to do, I want to push the address, which is a print memory. We're pushing the address, then the size, right? And then I'll have to write that entire thing. All right, so we debug. I mean, the debugger is implemented by Hertzon plots. All right, so here is this thing. Here is this thing. The book is telling me f minus k u. Cool. I'm really glad that that's what it's telling you. So, and let's call right. Oh yeah, and that's exactly why I implemented this thing. Yes, so you have to do native. So now it even tells me that I'm doing something incorrect. So yeah, I can never make the same mistake ever again. Debug, run, and it printed 6. It printed the first 6. Isn't that amazing? I think it's goddamn fucking amazing. And I think we ended. Yeah, I think we essentially ended on the. Yeah. So let's actually go a little bit further. It's kind of. All right, so let's try to execute BME. And it didn't even print anything, did it? I'm not sure. And then it goes here. Okay, so it printed some stuff. Okay, it printed some stuff. I think I need to go here. Let me go here and see what's gonna happen. Let's go to BDB. Illegal instruction. No. Illegal instruction access is okay. It's okay. So run. Let me take a look at the stack. All right. So this is exactly the reason. This is exactly the reason because we have some garbage on the stack. So if you try to drop all of this garbage on the stack, leaving only the return address, it will actually print everything correctly. So let's actually try to run it. BME I, and let's see. Cool. 694. It printed the first fraction digits of the fraction, but it didn't print 2 because there is a last part of the algorithm that needs to check this kind of stuff, right? It needs to check this kind of stuff. But apart from that, it works correctly. What's interesting is that once you break out of the algorithm, you're gonna end up with this thing yet again. You're gonna end up with UMR one more time, and you will need to check R to decide whether you want to increment U or not increment U. So let's actually check it out. So here's the debug, and this is not what I wanted to do. Zozin BM build, so it's gonna be BME, and instead of BME I'm gonna do BDB, break debug. Okay, run, and here it is. So this is the last digit that we need to print. We printed 694 and we need to print the last one, 2. So this is the precision that we've got, and this 0 value I think is the rest of the digits of the fraction. As you can see, we exhausted all of the digits of the fraction. So that thing is going to be has to be actually written then later, like dropped later before jumping out. All right, so what we need to do, we need to bring R, so 0, 1, 2. So we'll have to do dupe 2. So that should bring the fraction to the top. So we're bringing the fraction to the top. Bring in debug, run, start. Cool. So we bring in the fraction. Did we actually bring the fraction? I think it has to be brought to the fraction. Yeah, I think everything is correct now. After that, we have to push half. Push the half. So this is going to be the half. Right, we're pushing the half. And let me double check that everything is correct. So here's the fraction, here's the half, makes sense. And after that, we wanna skip the let me take a look at the assembly. I think in assembly it was a little bit better. Skip increment. When do we skip the increment? When r is greater than half, we increment it by 1. So that means opposite. Less or equal than half, skip the increment. Less than or equal than half. Less or equal than half, skip the increment. Okay, so that means we have to less or equal like this. And I think this has to be false in our particular case because r is equal to 0. Alright, so that's kind of cool. Alright. What book are you using? Can you type it, the name? I'm not using book. I'm using white paper, like paper from this from the ACM journal, I think. I'm using. Oh my god. This one. So yeah. So just look up for this one. It's not even it's from a conference from 1990. That's what it is. It's like an article. It's not even a book. It's just an article on how to print floating point numbers. Yeah. So. All right. So, and by the way, you can find it in like open sources. Like you can just Google it up. It's available, I think, on GNU somewhere. Yeah. Let me see. non-gnu.org. Okay, I don't remember what is non-GNU website. What is non-GNU website? Some kind of fishy website. Ah, things like Savannah. Okay, well, yeah. There's no. My point is, there's no pirating here. Okay, so everything's okay. How long are you learning assembly? My entire life, and I'm not even joking. Okay, this is true. That means, okay, it is less. That means I need to skip +1. That's true. Okay, GMP, if print frac skip inc. Okay, and we have to do printf skip inc. There we go. All right. So, and then here, since this entire thing is consumed, we'll have to do push one. Actually, no, yeah, we'll have to do just +1, right? It just has to be +1. Push 1 plus f. Right, so, and that just increments that thing, but if it's good enough, we will have to skip it. All right, let me see if everything's okay here. But speaking of assembly, this is my own assembly. I created my own assembly for my own virtual machine. You can find the source code of what I'm doing here, actually. So it's not like an existing assembly. I made this thing myself. First of all, I designed a virtual machine that executes a bytecode, and then I made an assembly for that virtual machine, and I'm programming for that virtual machine in that assembly. So these instructions, these are not like Intel instructions or anything. Like these are completely made up instruction. Completely, they didn't exist before. So yeah, that's what I'm doing. Can your regular Twitch streamer do that? Well, depends on definition of regular. I think I can name like a bunch of Twitch streamers who can do this thing that are doing, and even probably better. So is your throat okay? I don't think so. I think I just was talking too much. So yeah. Procoder depends on the definition of professional. Okay, so all right, let's continue. So we're skipping this thing, and we should essentially end up. Yeah, I need to break on debug. And this is the digit that we have to print, right? This is the digit that we have to print. And I can copy paste this stuff for printing digits, right? So it's essentially like this, right? We're gonna just put it here. And okay, so that will print the last digit, hopefully. I don't know why I'm building it here. It doesn't need to be built here. Break debug, run. So it already printed 69 for 20, and we end up with a bunch of shit on the stack that we don't need. So we ended up with the precision and the exhausted digits that we now just need to drop, right? We just need to drop them. So if I drop, drop, as you can see, I'm doing drop. Okay, so I accidentally tested it properly. Yeah, so now it actually printed the digits of the fraction. Amazing. So yeah, if I try to do something like BME, like this, it just prints the digits of the fraction. There. How about that? Isn't that amazing? I think it's goddamn fucking amazing, mate. So yeah, we can now print like digits of the fraction and whatnot. I wonder if we can increase the precision. Can I set the precision to 6? Because I think it's like not enough precision to print everything. But yeah, I'll have to probably rebuild everything. And well, it doesn't really have to print that last 0. Okay, the thing I wanted to print, I wanted to go to my test thingy and also try to print something like push 1 2 3 4 5 6 7 8 9, maybe even 0 here. Let's try to add 0 and see how well it will print all of that. So I'm gonna actually remove all this thing here. Yep. Okay. Yep. It printed 0, 1, 2, 3, 4, 6, so it printed exactly 6 digits of the fraction, and the reason why I did that is because the precision in the standard library is set to 6. You see? So, and let's set it to 7 and see what's gonna happen. Can we set it to 7 and increase the precision of the printer? And we managed to do that. Oh, look at that, it's actually printed 1, 2, 3, 6. Because the value after 5 was 7, so it rounded it up. Look, it actually rounded it up properly because 7 is greater than 4, so it incremented the next one by 1. So, yeah, that's actually pretty cool. I wonder how much we can increment precision, so if it's gonna be 4. So, that's pretty cool. And that is implemented in Bosom, so that means it's going to be cross-platform, so it will work on all of the platforms for which we implement the translator. Imagine implementing printf and Bosom. Shouldn't be that difficult. I think the difficult part of implementing printf and Bosom is implementing the floating point printer, and we did that already. Okay, so you can actually keep incrementing the precision. So alrighty, so and now we have 9, 0, 1, 2, 3, 4, 5, 6, and 7, 9. And what about 10? So I think we can keep incrementing the precision. I think we can have a pretty good precision here because we are using doubles and whatnot. So I think like precision 10 should be good enough, right? Alrighty, so we have a fraction. How about that? I think that's goddamn fucking amazing. Okay, so here's the translator. Yeah. So when I'm building this entire stuff, am I building x86? Let me see. So it could fail on some of the places. Yeah, so we still need to implement some of this stuff. So we need to do Jeff. So let me quickly stop some of these instructions to make it work on x86, x64. Printf 1, 2, 3, 4. Fix me. Jeff. Alright, so what's another one? We need Zor. Break. Like that. So it's gonna be to do Zor. So yeah, different kind of conversions between this stuff. Oh my god, it's gonna be so fun to implement all of that in assembly. Holy shit. Oh boy, where is my soy? Okay. Printf 1, 2, 3, 4, right? Okay. Fix me. F2i. Has to be a pointer, of course. Let's go in the line. I to F. How many instructions did I use there? Minus. Okay. Apparently I used a lot of instructions there. So minus. Oh my god. Oh, I guess I don't really want to do that right now, but yeah, I guess I need to do that. Yes, I just need to stub all of these instructions. Maybe I need to do that like for all of the instructions, right? So it doesn't, yeah. Left. Div. By the way, how everyone is doing, so I'm gonna be doing that for a while, I think. So how are you guys doing today? What are you guys working on? What are you guys drinking? What are you guys smoking? I don't know what to ask. Printf. Not good, man. That's a little bit sadge. Not gonna lie. Just a little bit sadge. Whoa, virtual machine, impressive. Thank you. Yeah, thank you so much. Okay. I can't send any messages apparently. This is really strange. Just a second. Something with the cell phone service right here, right now. Like I literally cannot send any messages. Maybe I know what the fuck is going on. Not sure. So let me see. Ricky Border, it's not early here to drink anything fancy. I see. Why no hair? You are particle smoking. Nice try, KBG. It's just a tea. I see. Where it's sodium feels. Consider writing the macro that converts the salt into fix me. No. I haven't drunk enough water today. Yeah, I think me too. Yeah. All right. Alrighty, it's kind of strange, not gonna lie. I think KGB is onto me because something like really strange with the cell phone service. But yeah, let's actually write this macro. I think it could be a good idea. So how are we gonna do that? So you'll have to think how to do that. All right, we're gonna search for inst instruction. Then copy paste this thing. You have to be a little bit careful, right? So it's not gonna work that easily. Inst, right? Then you select that, then print f 1 2 3 4, right? Fix me, new, and then you save that, and that should give you the thing. And it didn't work. Nice, thank you very much. Okay. Oh fuck. Oh shit. Oh fuck. Everything is broken. Okay. Inst. Well, okay. Assert. Break. Inst. Oh, for fuck's sake. Print f. Okay. And it's done. Okay. Waste of time. All right. So now everything looks okay. bm.h. So what I was doing. I wanted to commit everything. Yes. So frac precision. This is why I don't listen to the chat, right? Because they don't know what they're talking about. Okay. So, all right. Implement print frac. Right. Implement print frac. To do for better include error messages. So this is one thing to do here. Okay. Stub more instructions in x86 64 translator. So that's pretty much it. Okay, so we're ready to implement dump f64. We're ready to do that. So that's gonna be fucking exciting, I'm telling you, chat. That's gonna be fucking exciting. So where do we have like dump i64, then we have dump u64, and so on and so forth. So yeah, dump f64. So essentially what we need to do here, we need to take the value, right? Of course, it's gonna be swap1. Okay, so it's gonna be return, then the value, and we swap it like that, and this is what we get. Do we have debug? Okay, so I'm gonna actually bring debug right here. So let's see. Alrighty. So BDB break debug. Oh, and I also have to go to the test, I think. Okay, so what we're gonna do here is we're gonna actually push 69420, and we're gonna try to dump f64, right? So yeah, we're gonna try to print that value and see how it goes. All right, I'm gonna recompile that. Maybe the recompilation was not required here. So native, and where is my stack? Here it is. Yep, can I do something like rl wrap? Yes, break debug, so I can now have this kind of stuff. Run, and if I take a look, we have the 69420 here. So essentially, what we need to do, we need to duplicate this entire stuff, dupe 0, dupe 0, and take the floor of it, if I understand correctly. Do we need to take the floor of it, or do we need to... we have to truncate it, right? So we have to truncate it. Trunk. So to do that, we have to do F to I. Okay. So. Can I do it now? All right. Interesting. So F to I and then I to F, right? And that will truncate it properly, hopefully. So let's see. Let's see. And afterwards, let's do it like this. So it's going to be print debug, run, and there you go. So we have 69 for 20, and then you have just 69. To be fair, since I'm going to print that, I don't think I need to convert it back into the float. So what I can do now, I can just do call print positive, right? So I can print positive, right? And that will consume this entire thing. That will consume this entire... why am I doing that? I don't have to do that. Okay, cool. So break and debug, run, and as you can see, it already printed 69. And now we need to print the fraction of this thing. How are we gonna print it? Well, first of all, I need to print the dot. So like after the integer part. So I'm gonna be pushing dot. Actually, I have to push the address, print address, print memory, and the dot, and I have to save that into the memory, right? So I save that into the memory, then I'm preparing the address yet again, then I say print a single character, and I do native, right? So that will print the dot. So let's see if it worked correctly. And it printed 69 dot, and then yeah, the stack is correct. I can say that the stack is correct. After that, I need to call a fraction. I need to extract the fraction out of this entire thing, right? So let's see if it's gonna work. Okay, bdebug. So it printed 69, and now here's the fraction. Cool. And after that, what I need to do, I just need to call print frac. And that's actually pretty cool. Call frac, print frac. Call frac, print frac. So after that, I'm doing this thing. Debug. And we already printed 6942, which is pretty close. And at the end of the stack, we just have the address, the return address, and then we return it back, and then we're halting. Perfect. So, but we also need to print a new line, right? We also need to print a new line after all of that. So it's actually pretty straightforward. I can copy paste this thing here. Yeah, print a new line, but instead of this thing, we have to put 10 in here, right? So let's just put 10 in here. Alrighty, and let me see. Debug. Oh my god. Okay, so let's actually do that without all of that stuff. Okay. It's printed 69 for 20. We implemented the print floating point printer. I know nobody gives a shit, but we implemented floating point printer entirely in Buzzin. Yeah, that's pretty cool. Yay! Congratulations, Zozin. Cool, got coder first try. Anyway, so I think we still need to have a special support for negative numbers. I think special support for negative numbers, because if you push a negative number there, right? So it's not gonna work. It's gonna give you some bullshit that you didn't expect, right? Okay, cool. Dump F64. Should be pretty good. Should be pretty good. Okay. So, and okay. Yeah, so it printed. What the fuck is this shit? Yeah, it's kind of interesting. So first you need to check if it's a negative number, right? yeah, first you check if it's a negative number, and if it's a negative number, you print a dash and whatnot. All right, so let me see how we can do that. Let me see. So this is where, so this is dump I64. Let me see, dump F64. This is what we do here. So we duplicate 0 before doing anything. All right. Cool. So I can start with here. So I duplicate this entire stuff, right? So I have X and rat. I duplicate it. And I want to also push 0. So this gives me 0. And then I need to check if it's less than 0, but if it's greater or equal than 0, actually greater than 0, right? If it's greater than 0, wait a second, I think I have a better idea. Wait. So I can push -0 and then do something like end B. Wait, do I have like end, but not the, I forgot how it's called in BM. Beat end. Do I have a beat end? I don't think so. And there's end B, and I think, is it the beat one? Yes, it's a beat one. Okay, so end B is the beat one. Nice. That's cool. So then I do beat one, and that gives me that. And you know what that means? If the negative flag is set, it's gonna be true. So okay, so then we need to negate it. Do I have not? Not. I think not is like the logical not. Inst not. It is in fact logical not. Okay, so then I do not. So this is going to be not that. And jump if skip negative dump F64. Yeah, this is actually pretty cool. So this is basically checking for the negative sign, right? That's pretty pogue, not gonna lie. Right, so we skip the negative, but if we don't skip the negative, right? 1, 2, 3, 4. What we have to do here is basically push -1. Well, you can always push 0 and then XOR that thing. So it's gonna be -0, and then you just XOR with that thing, and that will basically negate it for you. That's essentially the negation. But that's not enough. You also have to print the dash afterwards. Right, you have to print the dash to indicate that it's a negative number. So let's actually put this thing here. Maybe I need to extract print character into a separate function because I use it so often. Right, so I use it so often, and yeah, it would make sense to have it as a separate procedure here. Yeah, so I think that's the way to print negative numbers, and B is not implemented. And oh yeah, there we go. So now I can use this macro, right? So because I added more instructions to support. Okay, so let me run it, and is it gonna work? Is it gonna work? It almost worked, except I should have actually printed minus instead of dot in here. So let me see. Look at that, chat. 69 for 20 minus 69 for 20. Isn't that amazing? We have an actual printer for floating point numbers. 69 for 20 minus 69 for 20. What's interesting is that I think it will even support zeros and minus zeros. Right, so we could just push 0. Let me see what's gonna happen. And of course we're gonna call dump F64. Chiroptical, thank you so much for 19 months of tier 1 subscription. Thank you, and welcome to our Epic Assembly Club. How about that? Isn't that amazing? I think it's goddamn fucking amazing, mate. Thank you. Alright, so let me recompile this entire... I don't think it's needed. So we're gonna recompile it here, and... Yes, it worked. It even supports -0. It does understand -0. But it doesn't support none and infinite, right? So for this kind of things, we probably have to have a separate support. But I don't think I want to implement it right now because it's probably kind of boring, not gonna lie. Alrighty, so let me go to the BM, actually to natives HASM, and add a to-do. Dump F64 does not support nan and inf, right? And for that we'll have to have like special strings that do all of that stuff, and it's just kind of meh. So yeah. Anyway, so let me go ahead and commit whatever we have already. So yeah, this is the whole implementation of this function. And do I have debug anywhere? Okay, I think I removed the debug. So that's a lot of stuff. This is the whole standard library, 355 lines, and yeah, so a lot of stuff here is implemented purely in Boson, purely, without using any like direct assembly or anything like that. So yeah, that's pretty pogue. I like that. Okay, now 130 implement dump F64, 130 stub more instructions for x86 64 translator. So we'll have to fix them at some point. That's pretty cool. Yeah, I'm super proud of this thing. Holy shit. It's like I implemented my virtual machine, and I'm implementing like libc from scratch in that virtual machine, including this algorithm and stuff like that. To be fair, that algorithm is not the most difficult one. I think it's the simplest one, but I think it's pretty cool. Yeah. Okay, so let's actually do a little bit of migration. All right, so now I want to deprecate the print F64. Right, essentially I'm gonna just remove this entire thing and recompile everything and go through all of the compilation errors and so on and so forth. Yeah, and where we use them, yeah, there we go, print F, yeah. So this one is gonna be just dump F64, dump M64, and dump F64, and I think it's still gonna fail because you have to use fun, yeah, so trying to invoke native function from a binding that is labeled. Binding for native functions has to be defined via native, yeah. So it's just more type safe thing. UMP, what do you mean by UMP? I'm sorry, I don't quite understand. What is UMP? Oh, yeah. Now I understand, thank you. So you see, our assembly is actually pretty, you know, helpful when it comes to finding bugs and stuff like that. So, and this has to be a call. It's another kind of UML. You having PTSD from your university courses? Alright, so let's actually quickly have a replacement. Call dump. There we go. Yes, understandable. I graduated 7 years ago. I still have PTSD from university, believe it or not. Holy shit. Like, I mean, memes aside, I think university is like a really traumatizing experience. Like, a really traumatizing. And I don't know. Okay. So, yeah, I do understand you, Yangu-sama. Alrighty. So I think we replaced all of this stuff, and I wanna see... oh shit, I think because we have a custom printing, and the precision of that custom printing is actually 10 digits, I think the pi number is gonna be longer this time. Yeah, I think that's kind of pogue. Okay, let's see. Because before our custom printer, we used the printf one, and printf one has by default pretty low precision. So, but this one is, should actually have a better precision. So examples, and let's take a look at the pi. BM. Holy shit! Yes. What is the pi number? Pi number. Yeah, it actually fucked up after this part, but I mean, it's close enough. I'd say it's close enough. So if you round it up like 6 to 3, and then after that everything is wrong, of course. So maybe if you add more iterations to the pi. Let me actually try to do that. Pi bosom, because I remember the amount of iterations is customizable. Okay, so it's not really customizable in here. Let's do const n, and it's gonna be n, and it's gonna be this. So I suppose this is the amount of iterations that we have to do. Yep. So what about making it 1 million? How about 1 million? I think 1 million could be interesting. Yeah, 1 million iterations. Cool, 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 cool. And will it be better pi? No, it didn't improve. Wait, what about 2 millions? 2 million iterations. Okay, 2 million iterations. Yeah, we managed to compute the next character with 2 million iterations. 2, and the next one has to be 6, but I think, yeah. What about 5 millions of iterations? $5 million of iterations. Well, it's getting closer. It has to be 6, if I remember correctly. After 92, it has to be 6, so it's definitely getting closer. All right. So what about 10? 10 millions of iterations. All right. By the way, this example of pi computation was not actually implemented by me, so it's somebody submitted that at some point. Nah, it's not getting closer, unfortunately. I don't. Yeah. So because we're using like a not very good method. There are methods that actually approach pi faster. So this one actually approaches like pi in like very slowly. Yeah. Anyway, I think it's good enough. All right. So this one should be a little bit faster. What about E? So E, yeah, it's also good enough. Cool. Nice. So, and also, when I'm compiling everything, am I compiling? Yes, I'm compiling x86, 64. So, and in the native, right, I'm completely removing this thing. I'm not sure if we need print pointer. Do we even use it anywhere, ever? And we definitely don't need dump memory because we have write. And also, majority of these native functions could be actually removed. The only native function right now we really need is write. Right, so it's like nothing really needed that much. Maybe at some point we'll also add read that reads from the standard input, like writes to the standard input and reads from it, so we can interact with the user and stuff like that, and also read from the files and shit. That could be interesting, actually. So, and then grow the standard library over time. Yes, this is very, very interesting. Alright, so let me recompile everything, and let's do a committee, and maybe even then a pushy. 130 deprecate print f64 in favor of dump f64, and I'm gonna push that right into the repo. How many billion devices are you going to be running BM? Ooh, at least 3 billion, that's for sure. That's like the bottom line. All right, so at least 3 billion devices, that's for sure. Oh shit, I'm hungry. Okay. Deprecate printf in favor of dump 64. Sorting feed. We actually have a feed command. If you didn't know, you can try to use the feed command to feed me, I suppose. All right. Well, you have to provide an argument. Okay. So that's a lot of changes. Oh, thank you. Thank you so much for feeding me. I really appreciate that. Thank you, thank you, thank you. Look at that code. Look at that code. And it's all of that even works. That's the most amazing part. It fucking works. Holy shit. I'm so proud of myself. And also we need to do snitch report prepend body introduced in 141. So dump website does not support nan and inf. Yes, it is true. Oh shit, this is very important. So I need to replace some of the to-dos in the bosom to NASM. Query replace to do with fix me. This one, yeah, so that was a kind of a mistake. All right, so we need to report that. Okay, include directive does not report location if the file does not exist. Okay, so that's also important. Cool. So, and let's push that right into the repo mate. Also, fix me to do, and boom. Cool, 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 cool. That is so pogue. That is so pogue. All right, so we're waiting for continuous integration. Continuous integrazione. So what else do we have? Maybe I want to like report the location of non-existing include and whatnot. That would be, I think, kind of useful. I think that will be kind of useful, but I'm not 100% sure. Yeah. Let's just wait for continuous integration. Sorry. So we're still waiting for macOS yet again. macOS strikes again. Strikes. Fashion hacker is getting mad. Yes, exactly. That's exactly what's happening. So macOS, please get your shite together. So speaking of, how are we gonna do that? So I need to find the slurp file. Yeah, so arena slurp file. Basically, we need to be able to recover from the fail inside of arena slurp file. Right now, if it fails, right, it essentially just crashes the whole application. So we need to, yeah, we need to be able to recover from that. That's kind of important. That's kind of important. So, and I wonder how we can recover from that. Well, essentially, for all of these fails, so we can change the signature. So when if it fails, it returns the false, and we can have an output parameter here. So it's pretty straightforward, to be fair. So yeah, we can quickly do that. Okay, so merge pull request. Nice. Merge the pull request and delete the branch, of course. All right, so, but to be fair, I'm already streaming for 4 hours and I'm kind of tired already, so I think I'm gonna call it a day. We did a pretty good progress today, I think. We finally, we improved the compilation, like compilation error reporting, right? So now we provide the places where the entries are re-implemented, reset, and so on and so forth. We finally completely migrated the floating point printer to the bosom, so it's going to become more portable, right? So once we implement the translator for more platforms. Once we implement translator for more platforms, we will have automatically support for all of the separations. And yeah, that's super cool. But unfortunately, boys and girls, it is time for me to go. Thanks everyone who's watching right now, I really appreciate it. Have a good one, and I see you tomorrow. Tomorrow we're gonna do Advent of Code in Haskell, because tomorrow is Thursday. So every Thursday we're doing Advent of Code of 2019 completely in Haskell. So this is the challenge that we're following. No matter how much stateful code is required to solve the problem, it has to be solved in Haskell. And if you are into Haskell, join tomorrow, it's gonna be fun. Also, check out our schedule for more information on different projects and different streams we're doing and working on. Check out our WOTS channel where we archive all of our streams. These streams is gonna be there, but tomorrow we archive them on the next day. There you can find all of the playlists. For example, if you wanna follow the development of the virtual machine since the day one, there is a playlist there, right? So we document the whole development process from scratch. And also check out our Discord server for offline discussion with the community. And yeah, that's it for today, boys and girls. That's it for today. Love you all. Mwah.